this is technically 9 o'clock. Is everyone okay to start? Oh, hello. Is everyone okay to start now? Yeah, okay. Cool. Am I ready to start now? That's a question. Oh no. Are people still coming? Right. Okay, I think we are going to start as soon as this person walks through the door. Sorry, don't all turn and look at them. Sorry. Okay, I think we are going to start now. Wave. Okay. Hi, everyone. So welcome to PyCon US 23. I mean, unless you were here yesterday, in which case you already know what we're doing here. So, just so you know you're in the right room, this is the Exploring Eco Topics with Python. So that's me, Chiin-Rui Tan. You can call me Chin, like this. Okay. Tutorial roadmap. You can still hear me? Great. Okay, so hopefully you've got like all the files, as I have already been stressing. Hopefully you've got all the software and files. There is a lot. I'll talk about that in a second. But anyway, so we're just going to go through a couple of sort of ancillary things. The main bits are this, this, and this. I'm going to try and take 10-minute breaks in between. But like, I'll sort of consult with you. Like, we'll decide as a group how you want to use the time, because this is your time, right? So if you want to have more of a break or less of a break, we can figure it out. And then a wrap up, which is if we have time. It may literally just be like last line of code and then off to lunch. But anyway, we'll see. I'll introduce myself in a second, but I just want to like set the expectations. So this tutorial is about you adding some of the Python skills that can help you find out what's happening to our planet. And when I say you, because also there is a recording, as you know, I'm sort of saying you as potentially scientists, educators, students, researchers, policymakers, people whose livelihood depend on natural resources, people concerned, just citizens concerned about the next generation. So, yeah, for the wider audience who hopefully will be watching this, this is to kind of help everyone. And then when we say Python skills, or when I said Python skills, I was thinking of Python skills from the scientific Python ecosystem, so things like those. And then what's happening to our planet, I'm thinking particularly what's happening to the planet, which is our fault as humans. So more of the anthropogenic impacts that we are having. So there we go, some little emojis, which will signpost where we're going. So at this point, as a data scientist, question mark. I just wanted to, if you are willing to share, could I understand a little bit more about yourselves? Like, this could just be like a hands up. Anyone, people who are scientists? Oh yeah, okay, a couple, cool. There we go through all these like systematically, but yeah. Educators? No? Yeah, a little bit. Anyone want to volunteer who you are, what you are? Doesn't have to be like a long soliloquy, just concerned citizens, interested Pythonistas. Okay, that's cool. Yeah. Yeah, because it just kind of helps me shape, again, how we use the tutorial, so depending on your experience. So I guess the other thing I need to ask is your experience with scientific Python. Are people familiar with these? You have experience with them before? So previous experience, yeah. I don't want to like out people, like first-time newbies with scientific Python. No, okay, cool. Oh, this is going to be easier then. I can run through more of the tutorial faster. No, I'm joking. Okay, great. So who am I? You probably want to know. Oh, collage. Right, so obviously my name is Chin. I said that. I am basically a data science entrepreneur from London, specializing in open source outreach. I'd say people probably know, if you like DuckDuckGo me, you will see a lot of my community work. So originally in 2016, sort of starting Our Ladies London, which then became Our Ladies Global. And then more recently, some of the work I do with my startup around outreach to disadvantaged young people working in schools. mainly through sports, actually, analytics. So a lot of those references come up if you look at me to be like, oh, what has Chin got to do with eco stuff? So actually, what isn't publicly known is when I was head of data science at the Foreign Office in the UK government, I actually worked, and that was in 2017, I worked on a lot of these issues. So actually, international illegal wildlife trade, some sort of energy sustainability, Earth observation. I can't tell you too much because that was a security classified role, and unlike some people, some US Air Force National Guard, I keep official secret, so we won't go too much into detail what I actually did, but just know that I did do stuff. Now, whilst that was 6 years ago, actually, recently, in the past couple of years, the kind of two worlds have sort of merged, and actually, a lot of the sort of schools and young people I work with have actually started. They're like, okay, like Chin, the sports is great, but actually, we kind of want to know about like the disaster happening to the planet. So I've kind of actually started doing more of that kind of ESG sustainability work, culminating in today. Okay, so I don't know if you've seen this before. I find this a really useful diagram. But anyway, as you already have experience with scientific Python, a lot of people, just that'd be useful, like a little bit of a roadmap, a learning roadmap where we're going. So your tools, I'm kind of a bit like, if you really know scientific Python, I don't know what, am I going to help you learn something? Okay, never mind. We'll find out. So as you know, obviously starting with Python as the basis of everything we're doing today, Jupyter, which hopefully you have some experience with, and then obviously everything stems from NumPy, well, although obviously they would say that from this article being about NumPy. But so we are going to do a lot of NumPy, mainly under the hood rather than exposed. A lot of matplotlib for plots. Sorry, I don't know if you can see this. I'm like, ugh. So a good amount of pandas, some networkx, but also some stuff which is off diagram. So extending pandas with geopandas, which is the pandas geographic extension for pandas, and then using some of the other JavaScript functionality, just a little bit via Folium, and then a tiny little bit. We're using xarray and rioxarray. So xarray, which is basically labeled multi-dimensional arrays, and then rioxarray, which is the geographic extension of xarray. We're not, I'll just set your expectations now, we're not doing a lot, if you've looked at the test files, we're not delving really deep into the internals, and actually really internals of any of these. This is very much about using these tools, okay, rather than like what behind the scenes, all that kind of stuff. But yeah, specifically xarray and rioxarray to work with the satellite image data. Oh yeah, question mark. So, people, you're kind of familiar with some of these things? Can people tell me your experience with, you're comfortable with NumPy? You've worked with pandas? What have people done before? Nothing? Anything? Yeah? A little, okay. So it's sort of, people know what they are, so I don't have to be like, this is an array. Okay. Cool. I guess the other thing is, obviously, I'm assuming that you've worked with Jupyter, then people are comfortable with Jupyter. Oh, yes. Don't have to spend so much time on the other. Sorry, this isn't like, let me take shortcuts. But it's just, yeah. You never know what kind of experience people have in the room, so, and obviously you want to make it inclusive as possible. Okay, so let's preview the exploration outputs. Welcome. Can I get out of this? Come on, PowerPoint, work with me. Okay, so, excuse me. Right, where are we going? So we are starting with the wildlife trade exploration. Starts with CITES data, and then you end up with a network graph. So this is for pangolins specifically. Then we go to, in the second session, or second hour, hopefully, EPA, so Environmental Protection Agency. Sorry, I don't want to like teach you to suck eggs, but I don't know what you don't know, so I'll probably try and do more rather than less. Using some of the data from the Greenhouse Gas Emissions Reporting Program, GHGRP. So you go from that. We're looking at universities, particularly this sector here. So anyway, so that you can also use other stuff. And then we'll go. This is sad. The flashy bits are actually the like our least Python bits, but never mind. Is what it is. So we go to fun, interactive maps, and also boring maps as well. And then kind of more, I guess, traditional statistical graphs, but again, useful and stuff like this. And then the last section, we start with Landsat data. Well, as in the data, we're not doing the whole workflow, so as you know, you've already got the data sets which I prepared. And then we end up with a pixel-based image classification, sort of land cover thematic map at the Brazil-Bolivian border. Okay, so that's where we're aiming. I'm not gonna lie, I'm not entirely sure if we're gonna get through all of it, but we'll see. Now, okay, let's start. I have to find my actual Jupyter Notebook. So I think with that, okay, over to the coding, because that's why we're here. So can you please open up your Jupyter Notebook in whatever kind of IDE, or I am obviously using Jupyter Lab in the browser. I know you said people were generally okay with Jupyter. Do people need any, as in, can we just start going, or do people need a bit of a run through of some of the functionality? I'm gonna take that as a no. It should be quite intuitive, but okay, I'll just really quickly. So you've got the notebooks which are prepared, so you shouldn't really need to do much. You might, okay, if you are new, you might end up double clicking stuff like that. Don't worry about that, just run it. When I say run, use that, or do Shift Enter, because that kind of gets boring having to go back and forth. If you need to add more cells, it's like that. Delete is like that. You've also got, hello. I'm sorry? Oh, bigger, yeah, sure, of course. Più grande. Yeah, sorry, I should have done that. So 150. Is that sort of bigger? Yeah, sure. Yeah. Okay, perfect. So yeah, that's adding cells. You obviously you've got what do you call these controls here? Delete. Other fun things. So tab controls. So import pandas. So tab is great for autocomplete, and then shift tab for doc strings. Okay, whatever. So shift tab, we'll use that a lot as well, so we weren't done with that. Okay, so with that in mind, oh, I should also just double check. So can you set up, if you're in Jupyter like this, obviously however you're using it, please have the tutorial, the material is designed so that it's like you're just basically dumped in the same directory. So you've got your 3 notebooks, you've got your data's all, I know, free and easy out here. And then you've got the subfolder. This is for, obviously, the deforestation. This has got your 4 raster data files, and then that is the shape file, which was downloaded from US Census. But obviously, if you are, because this is not a beginner's tutorial, I presume you kind of know how to access, local. You don't have access to this, right? No, sorry. This is just like how it's sort of set up, as in how, like, in the notebooks, when I'm calling things, like the file path will be assuming that things are local like that. But obviously, depending on where you've put stuff, like maybe in downloads. But yeah, we can sort of run through that. I think also just before we start, 14 minutes, not bad. As you can see, I have no TA. It's quite lucky that I can even sort of be here, given the crisis which is happening in the UK in terms of cost of living. So if people have issues, as a room, like, I believe in democracies, you just let me know how we want to kind of proceed. So if someone has an issue, like, do you want me to stop and then I help them? Or like, yeah, stuff like, I think we're just going to have to figure it out as we go along. But to be honest, this is an easier crowd because, like I said, normally I just go into schools and with teenage kids who really have no interest in anything. So you are, honestly, this is like an absolute holiday. You're not trying to sneak out and have a fag, behind the bike sheds. You actually pay to be here, so. I'm kind of hoping that's why I was like, okay, maybe we can get through a lot more than normal. Okay, so we're just gonna go, okay? And we'll see how we go. Whew. Okay, so if you can open up your eco tutorial, wildlife trade exploration notebook. Oh, I should probably start at the beginning. Okay, so a blurb. I'm sorry, I also use a lot of slang. Are people okay, I was going to say, with the level, the pace of English that I'm using? Yeah, okay. Sorry, just want to make sure it's inclusive. I'll really try not to use slang, but I can't help it. Okay, right, I'll read off here. So, what example of wildlife trade are we examining? Trade from 1975 to 2022 of all 8 species of pangolins. People know what pangolins are, right? There's like artichoke. Okay, cool. Which become it became illegal for commercial purposes in early 2017, having been uplisted to CITES. Anyway, scientific approaches, we're taking our graph theoretic and network science approaches. What outputs will we develop? Network graph, data structure, and visualizations of this. What will our outputs tell us? They'll support identification of the countries most involved in the legal pangolin trade to date and the main international trading partnerships. Beyond the well-known eco-impacts of wildlife trade, so biodiversity loss, what makes this example significant? So pangolins are currently the world's most trafficked wild mammal, despite the 2017 global commercial trade ban. In fact, many sources report that illegal pangolin trade has actually grown post-ban with the expansion of criminal networks. So tackling their illegal trade is therefore an urgent conservation priority, and being able to identify the countries who are known to be most active in the legal pangolin trade, which is the aim of this example, is likely to have some predictive power in terms of tracing the apparently thriving black market. Okay. I know that also seems a bit schooly that I'm just kind of reading stuff up, but I have also designed the notebook so that it's basically all the material, so then you can use it as a resource like after. So, stuff on the data, or if you want to link into it. Okay. Okay. Section A. I should also just bring to your attention the table of contents. So, I mean, anyway, you can read that, that's fine, but just so you know where we're going. So A to F is where we are going, hopefully by 10 o'clock. Okay, A, set up Jupyter Notebook and pangolin trade data. Step A0, import the third-party packages, numpy, pandas, networkx, and the matplotlib pyplot submodule with conventional aliases. So, I've designed this so that we obviously type in together like an interactive lab, but obviously feel free just to like copy and paste. We may do that if we start running out of time. Or when the code doesn't really have a lot of pedagogical value for you to type it. I have not done that right. That's also not right. Cold fingers. Yay. My said it works. Okay, A1. Excuse me. For auto-completion, or if it's not working, try running this magic command. I'm just going to copy and paste because this is, again, not particularly exciting. A2. Read in the pangolin trade data, wildlife trade data CSV, and assign to raw data. So PD read CSV. Then you can do this however you want. This is just kind of how I tend to demonstrate. So I kind of go with the right-hand side first to be like, this is what we're actually loading. And then this is where we're assigning it. So, phew, that worked. That'd be awkward if it didn't. A3. Make a copy of raw data called dfprep. This will be the data frame we will prep and ultimately construct our network graph from. So raw data, autocomplete, copy. Oh, I really didn't need to bring that up because I knew that. Never mind. Prep. There. So again, that's, we'll do that basically every, what is it called? Notebook. Okay, section B, inspect the data. Excuse me. Have a look at the prep data frame using head method to display the first 5 rows. So, df prep. Okay, so as you can see, there is various columns. We're actually not using most of these. The thing really to note is, as I've said in the comments, this is a pandas data frame. If I read here. So, as you already know this, right? Two-dimensional, so rows, columns, labeled. Show the label. So, there. So that's the row label, and then the, oh, seriously. And then column labels. So, oh yeah, columns are potentially different types. Do you sort of know this already? Yes, okay, great. But okay, if you don't, I'll just quickly say. So yeah, what's interesting about pandas, data frames, as opposed to, for example, like a numpy array, is because you don't have to have homogeneous data types. So here, for example, you've got obviously string or object data, but also here, there's also numeric. So that's really handy. Okay. Oh, panic. The other thing to note is that not all the transactions have data for every column. So this has been marked with nans, which stands for not a number. So B1, let's just have a look at the number of rows and columns. So the interpretation of that is that the data set records 1,689 transactions where pangolin commodities were traded, which date between 1975 and 2022. So let's now look at the actual data types. Oh, sorry, I should say. See what type of data pandas inferred was in each column when it originally written the CSV. Ignoring my own notes, awful. So the object data type, as you see here, is one way that pandas store string data. There is another, I can't remember the name, but anyway, when you see object in our data sets, that basically means string data. Okay, section C. So I'll just give you a quick overview. So now we're preparing the data for exploring illegal wildlife trade, and then we've still got a couple of more data wrangly things to do. So the context for this, the original data request from CITES deliberately did not filter trade based on any recorded purposes. Let's review CITES purpose codes as per the database documentation. So these are all the codes. This is not obviously just for the pangolin data. This is within the trade database, the CITES trade database as a whole. Obviously, not all the transactions have complete data. So this is like where they got a purpose. This is what they categorize it into, but obviously not all of them have a purpose. So C0, access the subset of DF prep containing just the transactions driven by the types of demand that could be more likely to persist after a ban, i.e. hunting trophy, personal, circus, or traveling exhibition, or commercial purposes, as well as where this data is missing, and reassign DF prep to point to the copied subset. So just so for some intuition, it was sort of, again, if you actually did this, I guess for research purposes, you could do this in a more, I don't know, more whatever way, depending on your purposes. But it was really more just like, if there was a ban, like I'm assuming the scientific community wouldn't just like go underground, right? So I was like, which of these things might continue? But again, there isn't necessarily, this is only like partial data, so it's just illustrative. Sorry, yes, great. So, okay. So for people who haven't used pandas, seen pandas before, so, okay, sorry. So data frame, indexing operator, we're giving it a label, a column label in this instance, so that would pull out the column like that. That will not work. We want to see basically, is it in this list of stuff? Again, you can see this in the code detail, which I'm not going to talk through. It's, again, just for your reference. But I apologize that it's a little bit busy on the slide, but, more information is less, right? So basically, let's bring out a Boolean for where the values are in one of these strings, P, Q, which are the purpose codes, and then nans as well, of which there are lots. So there we go. There's your Boolean array or series, and that's how we're going to cut the data prep data frame. So now we should only have the rows where that term, what was it? Purpose even. Without purpose. So there we go. Nans, T, Ps. That's kind of what I want to see. Great. And then let's copy that. Copy even. Excuse me. So C1, let's sense check. So we should have less rows, right? So 1396. Great. Okay. And of course, it's still the same number of columns because we didn't do anything to that. C2, we need to be able to quantitatively compare transactions in the data set in terms of the volume of wild pangolin specimens lost. So let's compute a quick histogram / frequency table of the term column values to see the different pangolin commodities traded. So data frame, we're indexing again by column label. The column label is term, which of course brings up that. Value counts, which if you haven't used pandas before is like the best. Oh, I am in love with this method. It's like my favorite thing ever. I use it far too much. So just so you know, the default is that the drop not equals true. So we're just going to override that. Although actually in this case it doesn't actually matter. But just, you know, illustrative. So you can see in this data set, again, this is just the number of trades which traded this type of product, right? This is not the number of products. There's no kind of like proportionality in terms of, you know, the scale of, like, was it like 428 transaction skins with 1 skin each versus like 1,000? But anyway, you get the idea. So this is just so you see what's in it and also a bit of the sample sizes. So unsurprisingly, we're also gonna, oh no, we're going to filter rows. Getting ahead of myself. I'll just walk through C3. As a necessary but imperfect approach to standardizing the trade, subset DF prep for the transactions involving commodities where each unit is more likely to represent one pangolin animal taken from the wild rather than a constituent part, i.e. skins, live bodies, excuse me, trophies and specimens. Be aware our remaining data will significantly undercount relevant traded pangolin numbers. So does that make sense intuitively? You understand what we're doing, that we can't, like, you can't compare like a skin scrap to medicine to a scale, like we just don't know. And obviously if you were doing this properly, you could use, you know, you create some sort of algorithm to figure out how you estimate a whole pangolin from some of these other things, but we're not. Okay, so again, we're going to pull out the term column, which is still that, is in. So pass it a list of the values, skins, live, bodies. Sorry, this is a little bit, it's a bit gruesome. But you know, that's what humans are doing. You know, my people as well. Or anyway, we'll talk about the country things later. Specimens. So that gives you a billion, and that's what you, of course, index the data frame on. Which then, if you can sort of see here, will give you less rows. So that looks sensible. Copy. And then, where's sign? Ta-da! Okay, so now let's properly look at the shape again. Sorry. C4, check that DF prep now has even fewer rows than before. I don't know why I write things out when I don't actually read it. So now we have 612 rows. C4 comment. We have cut the number of pangolin transactions in our dataset from 1,689 originally to 1,396 to now 612. Whilst the steps taken in this section to clean the original dataset have undoubtedly dropped relevant as well as retained less relevant data, these remaining 612 trade records are still a useful subset for demonstrating a Python-enabled graph-theoretic approach and being able to derive limited but interpretable outputs related to real-world illegal wildlife trade. Okay, so don't like give me feedback being like, oh, certainly, why did you do bodies? Why did you not do? It's like I know, this is not how you would do it properly, but you can always refine this, you know, method if you need to. So, section D, just show you quickly. So now we're going to prepare for network graph construction. So finally, we're moving towards the, you know, the fun, exciting part. D0 intro. As previewed, we are preparing to turn our pangolin trade data into a network graph where the nodes, vertices, represent the countries importing and exporting pangolin commodities, and the edges connecting them represent trade from an exporting country to an importing country. Have people worked with networks before? Do they? No? Okay, cool. Yay! I can tell you something. So, I mean, it's intuitive, right? I mean, okay, anyway, we'll go through that. There are multiple graph types. Please ask questions, by the way. I mean, not kind of like an hour-long lengthy questions, but, you know, if you need to. You're just not like disruptive teenagers. This is just very weird. There are multiple graph types. We will construct a multi-digraph. It is a directed graph with self-loops and parallel edges. And I will just bring this up because it is useful if you have not worked. Networkx is, I mean, networks are great. Sorry, I'm just like So this is just to give you a little bit of context. So a graph, okay, so undirected, basically it's like, so, you know, think, oh God. Okay, like as they are a sponsor. Okay, so think Meta, so Facebook, right? So Facebook friend, your friends, right? It's not, well, hopefully it's not just like one unidirectional friendship, because that would be like creepy and stalkery. But okay, anyway, so that should be, a friendship should be undirected, right? So that'd be friend, edge. Digraph, okay, maybe, oh, I don't want to talk about stalkers. Then you could have nodes, obviously, which could be directed, because it's like, you know, there is a direction. So, I don't know, maybe it's like a friend request, right? So someone sent a request to someone else, like a LinkedIn connection, something like that, say. Then multi-digraph, so parallel edges. So, okay, yeah, so say it's like LinkedIn, so maybe someone sent that person like multiple, I know you can't do that, but let's say like whatever, they send them multiple requests on different platforms or something, so you've got multiple edges from a node to another, excuse me, node. And then multi-digraph is, so again, that sort of parallel edges. It's basically everything, right? So it's directed. It's got parallel edges. So it could be like that way. And then also you can, like with the other ones, you can also have self loops. But we don't have that in the trade because you... So it's, I was going to say, in our example, because we wouldn't have it, but it's like, let's say Japan sold pangolins to itself. Do you see what I mean? So like it would loop back, but obviously that doesn't happen in our situation. But yeah, sorry, I can't give you. There's probably some better examples. I'll try and think of it. Does that sort of answer? Okay, great. Thank you for the question. Right, where were we here? For each directed edge, we designate the country who sold the goods, so export country, as the source node, and the country who bought the goods as the target node. So, is that right? So, sorry, I'm trying to give you your direction. So, you sold it to this person. Yeah. Source node, target node. Arrows are drawn from the source node, seller, to the buyer. Parallel edges of our multi-digraph will reflect a pair of countries who have made pangolin trades where one was the buyer and the other the seller, and vice versa. So, because actually in this instance, as you will see, excuse me. Okay, let's say Japan and Singapore. So, you know, obviously Japan can sell to Singapore, and Singapore can also sell to Japan, right? So that's your parallel edges between two nodes. Okay, D0. We can only construct a pangolin trade graph data structure from transactions with both defined source nodes and target nodes, or else it's just like source node to nothing. Our visualization also requires quantity data for each transaction, which we'll address after. First, check if any NaN values exist in either the importer or exporter columns, because then we cannot use them. So we're indexing again. This time, because we are indexing on multiple columns, we need to pass it a list with those column labels. So importer, exporter. That's not going to work. Sorry. It's going to sound really weird on the recording. Isna. Okay, sorry, I should do this in steps. Right, so pulls out the columns, great. Isna. Yes, no, well, true, false. Values turns it into an array. And then any, which is, I think that's, this is definitely a numpy function, basically says, are there any trues in that array, right? This is where your Boolean logic goes. Are there any trues in this array, true or false? So we want it to be false. And it is false, thankfully. You can also run this step, D1. I'll give you another way, which basically pull out the rows where both importer and exporter column are NaNs, but we won't go through that. D2, now turning to the availability of quantity data for each transaction, try randomly sampling rows of the data set, say 10 at a time, and maybe a couple of times, just because I kind of want you to see something particular in the data. Can't remember the default, oh, here we go, doc string, shift tab. So the default is 1, which is, I mean, cool. Okay, so I'm trying to demonstrate something. Okay, so right, so these are the columns that we are interested in this instance, right? Because we need to have a quantity value for each transaction. So you can see you've got nans. You can see sometimes you have the same data, which is really helpful if it's corroborating. Sorry, I'm trying to find. Okay, this is a really poor example, but here you do have two values, but they're not the same, right? There are some worse examples. Randomness. Like this, okay, this is a good one, isn't it? This is 5 times the size. So, you know, like, again, things you need to think about, how do we handle that? And D3, how are we handling that? Oh, okay, we'll do that next time. D3, find any transaction rows which are missing both importer reported quantity and exporter reported quantity data. So basically, like, at this point, we're like, well, even if you give us 2 values, that's still something to work with, but we can't work with no values, right? So let us, let's see where we have neither of these values, because we cannot use that. Importer, tab, yes, thank you, equals nan. That's not going to work. Nan. So I'm going to do this cheat way. So one condition, another condition. I'm just going to export. That will work, right? And then I am, excuse me, indexing on those multiple conditions. Oh no. TF prep. Sorry, bigger. Oh. Poor. Yep. Live debugging. Who doesn't love it? Okay, so you probably got there faster than I did. So thankfully, there are no transactions where there is neither of these data. So that's great, I guess. D4, construct new quantity data for every transaction where the value is greater. The value is the greater of the reported quantities or the only reported quantity. Okay, so my method to deal with this is basically like, whoever said there was more quantities, because I'm assuming people don't want to like be like, yay, I like took loads of pangolins out of like the world. I'm going to assume that the one who said more is probably more correct, right? The other one was like, no, there's just not that many. Don't worry, nothing to see here. So that is what we are doing in this code. So how did I start this? Okay, so we're creating a new column in dfprep. So think of this as like, if you haven't used this before, this is like, you know, creating a new dictionary key value pair. We're creating a new column called quantity. That quantity, excuse me, is going to be calculated by applying a function to dfprep. That particular function, which we'll use a lambda function, is basically going to be a nan max, which basically means take the max of these values and ignore the nans if there are any. So really great function. Thank you, numpy. Love you. Importer, that's not going to work. Imported quantity. So tempted really just to copy my own code. That's probably not good practice. Nan max, right. So those columns, and then you have to specify axis equals column. So basically tell the method to look in the columns for those labels because they're not in the rows. I do not feel confident about that. Okay, I'm sorry. I'm just going to copy my code because I don't want to create. I don't want to create a double. I don't want to create a quantity column twice. That is not what I prepared for. Okay. Right. So quantity. So sense check. Yes. I mean, we could, you know, maybe we should look at some other things just in case. Is there anything? Okay. Well, anyway, I can't find that example of like where there's 2, but it works. Okay, section E. So here we go. We're really getting more into the network stuff. I know, sorry, it's that data sciencey thing where it's like 80% is the wrangling, isn't it, before you can actually get to the good things, which take literally 5 seconds. Construct edge lists. So intro. An edge list is a data structure used to represent a network graph and is a listing of adjacent nodes. Our edge list will differentiate between the source and target nodes, which is a necessary distinction for directed graphs. We will also include the new quantity data for each edge in our edge list, so quantity, which we'll basically use to like change the widths. As I said there, this edge attribute will be used as weights. E0, construct an initial edge list called edgeListRaw by copying the subset of dfprep with just the importer, exporter, and quantity columns. So dfprep. So we are just, oops, why are you there? We're going to pull out those column labels, importer, exporter, exporter, quantity. So there we go, those are our 3 columns. Oops. Make a copy. Edge list raw. And then we can have a quick peek at that. So, cool. Okay, things I'm about to point out in the next section. So, you can see, not surprisingly, you do have like multiple transactions between the same exporter and importer. So E1 context. Whilst we could construct and draw a multi-digraph from this edge list raw as is, the visualization would obscure significant edge detail. So repeated directed edges, so like those ones, between a pair of nodes, such as the 2 transactions from the Netherlands to Great Britain, when both drawn with the same default line, drawing in the same position, it will look indistinguishable from a single default line representing a single directed edge. And then even if the line widths could be drawn with varying widths, in the case of multiple edges, only the widest width would be visible, dwarfing thinner lines. Does that sort of make sense? That's a really lengthy description, but I don't know how to explain it any faster. So yeah, we will therefore create another edge list with just the unique pairs of source and target nodes. So I just one reference of NL, GGB, for example, USG. Oh no, there's not a double. Anyway, you get the idea. I'll create another edge of just the pairs of source and target nodes, i.e. particular exporter, importer, with an aggregate quantity metric, namely the totals of the quantities recorded in all the trades made between each particular exporter and importer. This is why it's like writing stuff is so painful. E1, create edge list unique, a data frame produced by performing a group by operation on edge list raw, which groups rows by unique exporter and importer combo, sums the row quantity values within each group, and then also renames the quantity column as weight. I swear, all these things are just like so much easier like to actually just demo, but anyway, for learning purposes. Okay, so group by. This is our first group by. If you don't use group by, you should. It's really cool. So this is not going to give us much because you have to like give it a kind of like action on it. So in this case, we're going to do sum. But again, if this is you haven't seen group by before, you could also do all sorts of things like count, which will just tell you the number. I mean, it's not particularly relevant in this case, but I'm just showing that there are other things, minimum, max, etc., etc. Did I actually give you a max? Oh, well, anyway. But anyway. So we're summing it. I'll just do this before I forget, because I forgot this in one of my practice runs. So you can see here, it has the group by operation has automatically shifted exporter and importer into the index, or basically created a multi-index, but we do not want that. Please do not have that, because that messes up your code later. So pass as index equals false. So now when you do that, now it's just not normal, which is great. Sort. Now I want to sort the values, because as you can see, there is the sorting is by alphabetical, by I guess exporter, which is not particularly useful for us. Sort no values by quantity. The default is ascending equals true, which is never what I want. Maybe it's what you want. I don't know. Hope it works better for you than for me. So ascending equals false, and then finally, in this like massive chaining operations, which I guess is my laziness, rename the quantity column quantity as Wait. Please tell me that's the end. Oh, no, it's not. I haven't assigned this. Unique. Please be right. Please be right. Okay. And then have a look at it. Great. Okay. So, long and convoluted. Anyway, so now, as you can see, now we don't have duplicate edges. I mean, not duplicate, obviously, technically, because they're different transactions, but you get the idea. Even a comment, the row dimension of this resulting edge list tells that there are 138 unique pangolin trading relationships in this network. And then optionally, you can sum this to see how many, like basically what that adds up to, but I won't do it. But anyway, just so you get a sense. And then remember, that's also undercounting. Okay, section F. So here we go. We're really finally getting into the drawing-y bit. Construct and draw multi-digraph. F intro. From this point onwards, we start to use matplotlib in the tutorial. Be aware that there are a variety of styles / APIs available for accessing matplotlib functionality, and this is reflected in the tutorial. There are some cheat sheets. Sorry, I have opinions on matplotlib, but I shouldn't share them. Do people use matplotlib? Yeah. Oh. Sorry. I really should say that. Anyway, it's, again, grateful that we have it. F0, create a multi-digraph object using the networkx function from pandas edge list. Okay, I'm going to break this into steps. From pandas. So thank you, networkx. So they've made that really easy for us. Okay, so then you need to pass in required inputs from the edge list unique data frame, as well as optionally specifying the weight column data as an attribute of the edges and the graph type to be multi-digraph. So this is the data frame we're using is obviously edge list unique. We're saying the source nodes are the exporter column, the target nodes are the importer column, and the edge, we're giving it a edge attribute. Obviously, not all of this is, how are we doing for time? Oh, pretty good. We're going to pass that weight. And then we're going to say create using the multi-digraph. Oops. Okay. Create using annex. Okay. So F1. Finally, we can do some visualizations. Use networkx's basic matplotlib drawing functionality to try a minimal visualization of our pangolin trade network G. So this is where you discover if you created this correctly. I'm not entirely sure. So this is literally your absolute MVP, minimum viable product. It's like all the defaults. And it's going to look ugly, although you know that if you did the test. Notebook. So we're giving it, here we go. So node positions. There are node positioning algorithms. You can obviously, you could set them yourself, be like this node is here, 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 here. I do that a lot actually in sports analytics, like a formation. But in this instance, we're just going to be like, the Spring layout can just decide for us. But of course, that means that it will be different every time unless you set a seed. So I'm not setting a seed here. So you'll see how that runs. Okay, so there we go. Ugly, basic graph. But, I mean, fast, right? Like, if you really had data in edge list, that would be really quick. Okay, so k equals 20. So this is, you can basically adjust this to, let's do like 5, so you can make that smaller. You can literally just play around, and it's more sort of mushy. There's less like force, or like 50, so then things will be more further apart, like that. So you play around, and then if you want to set a seed, which we'll do actually in the next section, so be like, okay, actually I'll do 1. So actually I still keep wanting the same, I want the same positioning, so it'll just keep giving me that. Okay, so you get the idea. That's ugly. We want to do some more fun stuff. So you're literally at the last section here. G, intro. FYI, networkx is not a plotting library, so as per the docs, in the future, graph visualization functionality may be removed from networkx or only available as an add-on package. And they highly recommend that people visualize their graphs with tools dedicated to that task. So, like, not matplotlib. So therefore, because constructing matplotlib drawn network graph X graphs has low transferability, I'm just going to use, well, we're going to use this section just to demonstrate ideas for fine-tuning network visualization, so not recommending specific implementations. So does that sort of make sense? Because obviously, if you were doing this, you might use Gephi, you might use, like Pi, I don't know. There's like, oh, in fact, there's lots of things which I referenced here. So, yeah, this kind of stuff, graph is, pi dot, that was it. So there are other ways you do it. So yeah, I'm just going to show you ideas, and then how you implement that in different packages would be totally different. So G0, don't bother typing this, just literally just copy and paste. It's just producing two arrays, which will they're just like helper arrays, which will help change. Oh, here we go. They'll be used to draw the edges of our multi-digraph with varying widths and colors proportional to their weight, i.e. quantity. So don't worry too much about that, but you can always deep dive. I think it is intuitive enough to understand. G1, draw a customized matplotlib visualization of our pangolin trade network with a plotting routine that exploits more of the available options, i.e. functions to draw just nodes or just node labels, etc., rather than just that kind of like draw networks. Blah. Okay, so obviously do this how you want, but I'm going to just sort of do it in a kind of absolute build up from nothing. Okay, so you do need a pos layout, because then that feeds in, you can see it feeds into these draw calls. So I'm going to give what did I say, k equals 40. I won't do a seed. Okay, so now I've got a pos. So you can draw nodes. The absolute basic is the graph and the positions. Those nodes literally do not have actually any labels, so you need to give that labels, which is node labels, which also needs G and pos. Then you probably want to draw some edges, or else you're just a bunch of floating nodes with labels. G, pos. What was the last one? Oh, okay. So that should work. So, okay, so there we go. So now you're basically at the last thing we just did in the last section. Okay, so we're going to work up from here and make it better. Okay, so, first of all, I'm going to need to make the fig size bigger, or else you just cannot see anything, because the nodes are all like lumped over each other. So let's increase the fig size. Let's give the... Should we start? Okay, I'll tell you. We'll start with the edges, because this is where we use that thing that I just made you create and didn't tell you anything about, which is really good practice. So this is where we're going to specify the widths now to actually the edge widths to vary. And then we're also going to change the edge colors again to vary. Color, custom edges. So that should work. So there. So now you can see, instead of just all those lines being exactly the same, they now, they don't necessarily look like they vary that much, but that's actually mainly because everything was sort of the same size, apart from basically this bad boy here, which was massive. So yeah, so this is on a scale of like greens to yellows to reds, but actually a lot of things were basically not a lot, so green, and then a couple of, just the one thing was like red. So that's where those two arrays I just told you to make without looking at are useful. And then, other things. I'm not going to type this because, again, this is not particularly interesting for you to watch. But yeah, then you can change nodes. Again, no actual labels. So, well, actually, no, sorry. There are labels, but the label default color is black. So you can't see them. So change the font, so now you can actually see. Sorry, I'm going to make this just smaller so you can actually see. What else? Anything else? Oh, arrows. Yeah, and then stuff like this. So because actually that's not directed at the moment. Your edges are just, your like friendship edges. We're friends, but this actually needs a direction. The min target margin. So what I've said is the target node. So the person who bought, the country who bought the pangolins, I'm giving that like a bit of a boundary. So you can see the arrows, and also it sort of differentiates the bar from the cell. So there we go. That's that margin there. I love matplotlib. I really do. Plat axis, I'm going to turn that off so you don't get that box. So there. So yeah, and like I said, stuff like that you can play around. That's just an idea of the different things you can do. You can also save that as well. But I won't, because I have about 1,000 copies of it. I guess we could probably talk about some. We should like interpret it, I guess. This is a really ugly layout. I'm going to try another one. Okay, slightly better. So yeah, interpretation. Okay, so again, I know we constrained our analysis, cut lots of things. We made a lot of assumptions, X, Y, Z. But within the framework of the data that we end up with, I thought this is really interesting. I didn't actually know this. I assumed when we were going to look at pangolins, I thought it was going to just be Asia and all the normal sort of, not stereotypes, but, things that people think about when they think about, people eating exotic animals and making medicines. But actually, as it turned out in this instance, so Singapore, Japan, Malaysia, they obviously are still involved, so, selling and buying. But actually what I thought was really interesting, and I did not, like I said, plan it at all, but actually the US bought a lot of pangolin commodities. They bought a lot of pangolin commodities from Japan, but also from lots of other places in the world. And there's also, okay, you can't see that well, but yeah, Great Britain also pretty complicit. France, quite a lot of things happening there. Mexico actually, was more than I thought. It was sort of surprising. Well, I don't know, surprising to me, but this is not my field, so I'm not an expert. However, of course, while saying that, some caveats, again, the interpretation. A few of the further caveats and considerations redrawing inferences from our pangolin trade network graph include possible range in the quality of trade monitoring and record keeping by country, as well as influential geopolitical factors. For example, not all countries are parties to the convention. I don't actually have data on their trade, or have been at all times. Plus, there were changes to country boundaries existence between 1975 and 2022. For example, if you are my generation, so the Czechoslovakia is now the Czech Republic and Slovakia. So, things like that. And then obviously maybe the US has more data on their trade rather than another country where they don't monitor so well, so on and so forth. Okay, there is the section H. Okay, we'll do it really quickly in 2 minutes. Yes? It's not necessarily what I would be suggesting, but I think there is probably countries who have better data quality probably are going to look worse in an analysis like this because they have, they have actually recorded those trades. They've kind of been transparent about their transactions. Whereas, there are other countries. Oh, this is a lot of recording. But, there are other countries, in Asia, for example, where I'm 100% sure that they are not, they're not going to be recording the data and or providing that data to, CITES, to the UN, so, yeah. Is that the sort of answer? Did you have a position on?
Oh, no, just because you stated that you had a very, you had assumed what the answer was going to be. The total opposite.
Yeah.
Right.
Yeah. So I think it's sort of, as you said, I had my preconceptions, and then this kind of was like, oh, I totally did not expect the US to be so. I could kind of see obviously from the data going through it, but yeah, I didn't expect it to be so dominant. But then obviously, then you also have to counter that and be like, but actually maybe there is more data collection and so on and so forth. So it's a balance, I would say. But yeah, I would definitely, if someone like worked on this, it'd be really interesting to see what other insight people had. Okay, we're really quickly just going to work through H just to show you that it's not just visualization, there's actually actual maths stuff. Okay, H0, I'm just going to whack this. So you can obviously just get out lots of metrics. There's like edges and, you know, so obviously if you just do G and then dots and then look at stuff, you know, there's other things. H1, okay, so I'm not going to read this through. I'm just going to tell you there are things like centrality functionalities. So that kind of gives you a sense of which nodes are important. But based just on, like, in this case, just based on like how many different people are they connected to, not the volume of their transactions. But like I said, it is just to show you that there are things you can do. And then, okay, this one I'll just really quickly show you. So if you sort that list and just take the top 10. So this is just about the degree of centrality, which means that the US, in this case, has traded, like I said, traded any trade, number of trades, in pangolins with the most other countries. So in this instance, 91% of the 55 countries in this network, which is 49 countries. But yeah, the other thing, which I sort of mentioned here, you'd want to look at is community detection algorithms could be a good next step, because you'd be like, actually, there are, obviously smaller communities within this. So US, Japan, Singapore, maybe. Can't remember what GQ is, not a magazine. XX is like the unknown, so, there's a portion there. But yeah, there could be sort of smaller kind of little regional relationships. So communities you want to look at. Okay, and that is your first exploration. Break time, I think, do you want 10 minutes? Yeah, okay. All right, I'll see you in 10 plus 10. Are we okay to start, like, now? Yeah? Okie doke. Okay, so I say that like I've been waiting for you rather than you've been waiting for me. I hope this microphone wasn't on when I went to the toilet. That'd be really weird. Anyway, sorry. That's a cybersecurity background, government background coming into play. Okay, so if you want to load up the Carbon Polluters Exploration Notebook, which hopefully you have. Honestly, I can't believe like, you all had the stuff. This is so smooth. You're so much better than like teenagers. Sorry, that's like damning with faint praise, isn't it? We probably do need to check. So we've got a little bit more data. So you should have, unsurprisingly, my verbose labeling. So you've got this CSV, but you also, need to have well, this is the shapefile. Yeah, that's like, there's nothing more I can tell you about that. So yeah, please make sure you have that somewhere you can access, because that's going to help us make, pretty maps. Oh, no. Okay. Someone's not here. Okay, anyway, I think we're going to start. Okay, so welcome to part 2. I think we're going to try and do this by 11 and then have a break just to set your expectations. So Carbon Polluters Exploration with Python. Note that you need internet access for section E, which is the interactive JavaScript maps. So, which sample of carbon polluters are we examining? So it is the US university facilities with large greenhouse gas emissions, which according to the EPA is over 25,000 metric tons of carbon dioxide equivalent per year. And so those facilities are in our sample if they reach that threshold in any year between 2011 and 2021. So 2011 because that's when the GHGRP Greenhouse Gas Reporting Program was launched, and 2021, as I said, is the latest reporting year. Have people heard of the GHGRP? Because I was going to say, I should also disclose, even though I worked for the UK government supporting foreign policy. I'm actually a US citizen, so this will come up actually in this this tutorial. So yeah, this is a surprise to me. I didn't know about the GHGRP, but anyway, lots of really good data, so I really hope this will incentivize you to look further. What scientific approaches are we taking? So we are doing statistical and geospatial approaches. What outputs will we develop? Oh, sorry, make this bigger. Statistical graphs and interactive maths with historical and or regional dimensions. What will our outputs tell us? Who and where are the significant US sources of carbon pollution within the higher education sector at facility and state level, both recent and since 2011? Beyond the well-known eco-impacts of carbon polluters, sorry, climate change, what makes this sample significant? So to me, it's the fact that this sector has, or individual universities are, large fossil fuel burners. So that might be a surprise, seemingly out of sync with any green credentials and reputation they have garnered, especially relating to clean energy. And so I also want to point out, so yeah, after I had sort of done this, or proposed this and developed it, I discovered this Reuters article. Again, I don't know if you're as excited about this as I am, because I was like, this is just really, I was like, these universities are naughty. But it turns out that, yeah, Reuters actually came up. They used slightly different data from a different source, but they were also, it's like the sentiment is the same. They're like, oh, look, these universities talk green, but they have dirty secrets. And also, I'll just point out, this is dated after I proposed this tutorial, so I did not take this. But it does corroborate a lot of the things which I thought were interesting. So I really urge you to have a look, because then they do a much more sort of in-depth analysis, because they're Reuters, so they had resources. But I also wanted to point out, this is my personal link to the story. So I don't know if people know, but I was there. So this is Boston. This is a facility, the Cambridge Alston Blackstone power plant, which, to be fair, Harvard only acquired in 2005, I think. What's really interesting, and I guess, so I don't want to dwell on the sentimentality of it, but what I find really interesting is that doing this tutorial, preparing this tutorial, I discovered that I actually grew up as a toddler. I grew up 2 blocks here from where this photo was taken. And I did not realize that I grew up under so near a excessive carbon polluter. So anyway, we'll talk about that later. But that just kind of gives you, there are real, obviously, I hope you know, there are real world impacts or real world, factors behind a lot of this data. It's not just, abstract. So yeah, I'm great, I breathed lots of fumes. That's cool. Maybe that explains a lot of things. Data source. So there's some background stuff if you want to know more about it, but it's all mainly government data, and that shapefile is from the US Census Bureau, blah, blah, blah. I shouldn't say that in my own tutorial. Sorry. Why is this? Okay, sorry, I wasn't sure why this was already there. Okay, cool. So I'll just go over the table of contents. So a bit shorter. Yeah. But different. There's a much more variety, I'd say, in this one than the last one. So A, set up Jupyter Notebook, university emitters, dataset, and US state shapefiles. So A0, import the required packages and submodules. Oops. With their conventional aliases. PD, import numpy as np. Import matplotlib, pyplot. Nope. Try again. Again, jig this. So if you are new to Jupyter, I know this seems tedious, but every computational notebook is, you kind of have to set up your environment all over again. So that's why this seems really boring, but necessary. A2, we are going to set a pandas display option to show all columns, not truncate the display. So because if you've got lots of columns, pandas will automatically cut out some of them just so you can fit more on the screen and put ellipses, which may not be what you want. A3, read in the university emitters dataset, Carbon Polluters exp data, and assign to raw data. So PD raw CSV, carbon polluters data, all data, and then again A4. If you create that prep data frame, although I just want we are creating a lot of data frames in this tutorial for reasons. And A5, it's just the other nagging reminder to please make sure that you have that shapefile as a subfolder somewhere you can access. I don't know if have people worked with shapefiles before? Yeah, okay, cool, some people, yeah. So if you haven't, I mean, I'm not an expert, I just use it for, I know enough about it to like do the things which I need to do. But yeah, if you actually open up, it's got other files in it, but apparently that is the shapefile. So anyway, it works. That's the most important thing. Section B, inspect the university emitters dataset. So B0, have a look at the dataset of large carbon polluting US university facilities. DF prep. Also note that instead of returning a default number of rows, you can start specifying the n argument. Okay, so comments. Like the original pangolin trade data, there is missing data we need to handle, like this. However, unlike the pangolin trade data, the data requested from the EPA flight data source is the exact sample of interest, so namely all the facilities in the US university sector with large emissions in any reported year between 2011 and 2021. So every row is therefore relevant, which was not like the case in the previous exploration. The required data prep, also called cleaning, munging, rambling, is therefore needed to modify the columns, not the rows, which is the focus of the next section. Okay, so B1, find the dimensions of DF prep. So shape again. So there are 118 US university facilities which were large carbon polluters in at least one of the years between 2011 and 2021. Did people know, like, I presume, some of y'all are studying in the US. Did you know that they have these big power plants burning? Lots? No? Okay. I was going to say, like, unless you're all like, yeah, obvious, this is like, because it really was a surprise to me. I think in the UK, I don't think, the idea of universities having a power plant is really unusual. So I didn't know if that was just, where I live, all my experiences. Anyway, section C, prepare the university emitters data sets. So C0, some of the columns are definitely not needed, so let's prepare to drop them and with some efficiency. Instead of manually counting, let's programmatically find out the index positions of each DF prep column. So you've got the columns attribute from DF prep. So that's the list of labels. There is obviously a lot, and we don't need them all. So this is just a really quick way to find out the index position of each one. Ta-da. So C1, perform a drop operation that removes 4 particular columns from DF prep in place. So subparts, change in emissions, that one, change in emissions, and then sectors. And review the modification. So we're going to do a DF prep drop method. We're going to drop columns, and the columns that we are going to drop have these index positions. So 10, 22, 23, and 24. And then we're going to drop that in place. And then we are going to see if they have gone. Nope, that's not going to work. Okay, great. And I guess another point to stress, as with everything in Python, is there are lots of different ways to do things. This is just a way. And I probably also should point out that the in-place parameter is accepted by several Panda methods, is used in this tutorial where possible for brevity, but its existence is controversial and currently in flux. So that's just to say that it's not considered best practice. So yeah, I'm not endorsing it, but it just makes things a lot faster. Okay, so C2, see what data type pandas inferred was in each column when it originally read in the carbon polluters data. So df prep d types. Okay, so a comment, pandas inferences are only partially correct. The columns that are essential to correct are the 11 years of reported emissions data. These are all currently object D-type, so basically string data, not numeric as required. You can also see here, these other ones are not, I mean, like, what's this one? Like, yeah, like an ID, this is not, I mean, it's really, I don't know, category or something, but anyway. There's other stuff which is not correct, but we're not going to worry about it because we don't need to. C3. Before we start modifying the 11 reported emissions data columns, let's shorten their long, cumbersome labels to just the reporting year reference. So we're basically taking out that stuff. Excuse me, and then review the modification. Okay, so DF prep, we're going to rename the columns to basically itself, but without this long cumbersome string, if it's in there. So take out, oops, no, jumped ahead of myself. Replace that string. So replace that with nothing, and then do that in place. Is that correct? Okay, so I'm just slightly not confident that I've done that correct, so I'm just gonna do that again. Okay, and then let's see what that happens after that. Excuse me. String be gone. There we go. Much easier. Okay, C4. Now start the process towards converting these 11 columns to a numeric data type. Remove the comma characters from the string data in these 11 columns, but not anywhere else in DF prep, e.g. reported address. And then review the modification. Okay, so does that make sense? So there's these commas which are, I mean, I know that it looks nice and readable, but is a pain. But we can't just take all the commas because there are actually commas here which are useful or relevant, although we're not using that data, but we don't want to touch it. So we are going to use the lock operator to do some multi-dimensional indexing. So we're going to take all the rows. Okay, so that would be all the rows and all the columns, right? Just in case people haven't done indexing with the lock operator before. Because we're using lock as opposed to ilock, we have to use labels. So we're going to use this label. And if I leave like that, that will slice everything from 2011 onwards, which is perfect. So that's how I'm selecting these 11 emissions data columns. Okay, so now that I've selected them, what do I want to do with it? I want to apply map. So basically take out the commas, or replace the values with itself, but without the commas. So lambda x. This is not lambda, apply map is not before anyone says, that's really slow. It is really slow because it goes through every element, but in this instance, it's, you know, we don't need like the fastest thing by itself. So that would take away your commas and then reassign to its override. Okay, and now let's see if that worked. Please have worked. Great. Okay, so, C4 comment, so this is just to tell you that these are just other ways that you could have done selected those columns, and there are obviously more beyond that. C5, the last string cleanup step is to deal with the -- instances in the 11 columns that we assume is EPA notation for nan, or sorry, not applicable. We will replace these string values in place with nan, and then review the modification. So this one is easier, just take out those weird dashes. You could obviously do some like fancier regex solutions, but you know, that's not really necessary here. So take out that. And take a look. Great. C6. Now convert the 11 columns to a numeric data type, and then review the modification by I. So we're going to use that lock method of selecting columns. So all the rows, and then all the columns from 2011 onwards, which is that. And now we can apply the panda function to numeric. To numeric. It's funny, it's only when you're like live coding data wrangling when you realize it doesn't, it's very difficult to make it fun. But anyway, it's necessary, and obviously as you're adults you sort of know that, and I don't have to tell it to you because you're, again, like I said, not disruptive children. Okay, so there we go. There's a deprecation warning. Like if you wanted to read it more closely, it's actually helpful. It's basically saying, I think in future you don't have to reassign it. It will just do it. Anyway, so it sounds good, whatever it's saying. But yeah, currently this is how we're doing it, and this works. So there we go. By I, this looks good because it looks like it's a float, but obviously C7, we should double check that that is actually a numeric data type, and there we go. It is a float, which is perfect. So C8, now we've got the columns with the 11 years of reported emissions data. Now that they are a numeric data type, let's compute some quick summary statistics. So describe, use of the describe method. So as I said, although we do have some sort of columns which shouldn't be numeric, but you know, we could have tidied that. You could obviously do that if you have more time. What is interesting here, I guess, just things to note. So count, for example. So this is like the number of US university facilities which, you know, met the threshold of being considered large, effectively carbon polluters. So 104, 103, you know, it kind of went up. I mean, again, this is not anything kind of world breaking, but, you know, just interesting things. It went down, but, you know, it's not, there's no sort of obvious pattern of, you know, dipping like 90s, 80s. So that's kind of interesting. Other things, I guess the mean you could look at, you know, again, you'd be hoping to see these kind of on a downward trend. So kind of a little bit, 81,000, 80,000, 77, but then starts going back up again. Again, I'm not saying this is particularly, it's not statistically significant, but it's not the direction you're hoping, right? Okay, anyway, we'll look at that in a bit more detail. C9, the subset of 11 emissions columns is time series data. Generate a quick matplotlib line plot. So we're going to select columns by a different way now. Select from -11 position, index position. So index df prep, excuse me, by that, which gives you those time series data. To do a line plot easily, you need to transpose. So you want to have your each row is the year, and then obviously along this is each university facility that way, and then you can easily plot. Oh yeah, that's why I said legend equals false. So there, again, just a really quick plot just so you can see. So yeah, you know, again, like, you know, Reuters and me, like, I think there's something, I don't know, this is just surprising that there's so many. This is the threshold, 25,000, we're assuming. But yeah, there's just a lot. This is really a lot. That's actually MSU, we'll look at that. And even though it's coming down, but it's like, I don't know. It was just interesting because I was like, you know, they're all like, oh yeah, look at, come and, you know, sign up for our masters on, you know, environmental blah, blah, blah. And I'm like, but look at you, you know? Anyway, sorry. Not like I'm like the perfect, you know, perfect green activist. Okay, C9. So there we go. But oh, okay, I said this, didn't I? Fine. C10. Okay, you could optionally check. You could check whether all those values are in fact above 25,000 or nan. So you can do it in your own time. C11. Final task for section C. Create a new cumulative column with the sum of each facility's reported emissions data over the 11 years. Review the modification. Okay, so we're making a new column. So remember, just like creating a key value pair for a dictionary. Give it a label. And then we're basically summing those columns. So access those columns, again, as the same way with the lock operator. Sum tell it to sum across the columns axis as opposed to the rows. Seems to be correct. Let's find out if that has worked as expected. Oh, phew, okay, yay. So you should have a cumulative column, excuse me, here. And then you could obviously sum that if you want to just see how much total carbon pollution these facilities have been responsible for creating. Oh, in fact, actually, I already figured it out for you. So 612, 11, Jesus, no, 118 US university facilities are responsible for approximately 96 million tons of carbon pollution from 2011 to 2021. Now, I don't know if that's, I can't give you any context for that, but that seems like a lot. Okay, now the main wrangling, cleaning is over. We can actually do stuff. Phew. I'll also just show you where we're going. So some basic mapping, then some interactive mapping, and then we do the kind of pandas statistical graphs, which I know are less fancy, but probably more informative. So D intro. For this mapping section D and E, we use the geographic pandas extension, geopandas, to create a geodata object. So a geodata frame is a pandas data frame that has a column with geometry and extends pandas functionality in order to make basic maps. Have people used geopandas? A little bit, yeah, okay. Okay, so some people have heard of it. That's helpful. I'm like, it's really a shame because it's basically all the JavaScript interactivity stuff, which really, that's the best way to engage people, kids with Python, not the actual Python, which is a problem. Anyway, D0, import geopandas with its conventional alias, which is GPD. Create a geopand, brain. D1, create a geodata frame called geodf using dfprep. Review the new object. So, GPD, geo, excuse me, data frame. Okay, so you pass it the prep data frame, and then we need to make some geometry. In this case, using the longitude and latitude columns in that data frame, the previous data frame. XY, pass at this column, longitude. So, and also remember, so points from XY. So, although everyone says lat long, right? Actually, longitude is actually the X axis and latitude is actually the Y. So, if you're doing geospatial things, obviously for people who already do it, then I don't want to tell you stuff you already know, but for people who it's new, just be aware that you're passing the right thing to the right axis, because that will really, you'll get some weird US plot kind of not on the right dimensions. TF prep, and then give it latitude. I'm snacks? Yay, thank you. Oh, that's service. Sorry, anyway. Okay, so actually I'll just run that just to see make sure. So I haven't assigned that yet, but yeah, so there we go. You would get the geometry. It doesn't look like much because it's just the lat and long, or long and then lat. But yeah, the stuff you can do once you've got that is really cool. Geo heads. So there we go. That is. Okay, perfect. So there we go. Points. And then now you've got those points. So D2, generate a default plot of this new geodata frame GeoDF, then try a customized plot where the color of the points is based on their cumulative column values. Okay, sorry, I'll do this. So we'll do this in order. GFDF, GeoDF plot. So this is your kind of quick and, I don't want to say dirty, but quick plot. So as you can see, those points are just like a 2D Cartesian space. But it does look like in the shape of the US, as it should. Then, if you actually want those points, for example, to relate to an actual column, you can pass a column. So now it varies, but we haven't chosen their colors, and they are not very interpretable. So then you can pass your own color map. Cool. So yeah, stuff like that. So D3, Okay, so evidently GeoDF plot needs a base map to contextualize the points. Load one of geopandas' available datasets, natural earth low res, assign to base map, then plot. So, file, GPT. So like I said, this is really the basic, you're kind of just using pre-existing sort of toy datasets. And then the next session we'll kind of do something more customized, but base map. But yeah, the point is also to kind of show you that it's like, I'm not saying this is obviously the coolest stuff in the world, but it doesn't take a lot of code. You didn't need a lot of resources, and you can create something which is, usable. So there we go. That's the base map. And then optionally, just to get a sense of what the geometry data represents and enables. Okay, I'm not. Actually, okay, I'll let you do that step. But this is just to kind of show you, like, those kind of geometries. When you look at the, there's me trying to be clever and skip things. So when you look at geometry and there's like polygons, multi-polygons, that's what those polygons are, right? Like, they're shapes. It's kind of the easiest way I can explain it to you. But I'm sure there's, geospatial experts who can tell you more. Okay, so there's also a CRS thing, which if you were doing more of this, you probably want to look at, but we'll skip that. So D6, use matplotlib to construct a basic map which plots GeoDF and basemap together, visualizing the location of the 118 large university emitters and the relative size of their cumulative emissions over 2011 and 2021. So as you can imagine, we're basically just taking those points and then putting it on that base map, and then it actually looks like something meaningful. Matplotlib, my favorite. Sorry, I have to stop having attitude. Okay, so let's set up sort of bare bones. Base map plot. It does need to be on axis though, or else it's not going to show. Then, so that's your background thing. Then your points, then you plot those on top, and then so that would work, right? Now you'd be like, oh, it really hasn't worked, but actually it has actually plotted those points, but because they're on the same default blue, like the west coast just looks kind of bulgy, right? So hence why you need to start doing some customization. So as before, column equals cumulative. Let's give it a different CMap. This is nicer colors. What else did I do? Oh, is that it? No. What? Cumulative. Autumn R. Sorry, debugging. Cumulative. Oh, sorry, I put it in the wrong call. See, why didn't someone? I'm joking. Your fault. No, I'm joking. Cool. Nothing better than live debugging on a recording. Autumn equals R. That's not going to work. So there, it's not going to set the word light, but yeah. Okay, I'll just make this bigger just to show that it is actually usable. So yeah. So like I said, it's not beautiful, but you didn't have to do a lot of work to get there, and does tell you stuff, right? Okay, so section E, this is where we basically do fancier version because of JavaScript. But you shouldn't say that at a Python conference. So section E, map dataset for regional trends, and this is the interactive version. So E intro, in this section we extend our geopandas extension of pandas with Folium, an optional geopandas dependency which provides interactive mapping from the open source leaflet.js library via pandas Python interface. So E0 import Folium. E1 test out the extended geopandas functionality that Folium now enables. So call explore on base map. So right, this is the same base map as before, right? But now you've got Folium. Now it's interactive. I mean, that's basically the same data, right? But it's just like flashy and does stuff. Okay, so E2. Rather than using a world map as a base layer to plot US-only data, let's prepare a regional map. Read in the US Census States shapefile we double-checked in section A, creating another geodata frame and assign it to US state boundaries. Okay, so this is where I've been like, make sure you've got the shapefile, because then this will not work if you don't. So pass in the file path to that SHP extension file. Like, you know, I never really understand why this works, but it does. It's some sort of magic. So, again, thank you, geopandas people. I mean, developers. Okay. So you could run that again. You could see what those boundaries, look like interactively. But, as you imagine, they are shapes of the US states. So, E4. Through a plotting routine, harnessing Folium extended capabilities of geopandas via GeoDF and US state boundaries, construct an improved version of our D6 basic map, namely an interactive map that visualizes the location of the 118 large university emitters and the relative size of their cumulative emissions over 2011 and 2021. Whew. Okay, so we'll do this again, just like bare minimum steps, right? So base layer equals US state boundaries explore, so it's that census data, like fancier. That's your absolute minimum. Then you take the GeoDF, which has got our points, the actual data we want to plot, and then explore. You're basically calling explore, but we're saying M equals base layer. So basically, like, put this on an existing map instance, which is that base layer that you just created in the line before. And then actually that's it. Then you can just call base layer, I think, as your absolute minimum, right? So again, default blues, it shows you all the data. But yeah, so that does work, but obviously, you want to customize that, and that's where all these other things are. So I'm not going to go through all of them because they are pretty intuitive. So if you do that, that kind of like customizes the base layer. So that's where I've just changed colors, made things like busier. Then this stuff here, these options here for the GeoDF Explorer are just to make the points more interesting, relevant, less irrelevant. So kind of colors things, and then only gives you particular information, not everything. Was there any other? No, and then you can save it as an HTML. Okay, so I'll just take this quick point to point out. So whilst through doing this tutorial, I discovered. So here we go. So Boston, you've got 4 university facilities which are large polluters, or at least within this 2011 to 2021 period, which are actually you can't click very well actually if you zoom in too far. But they're basically Boston University, MIT. This is that Harvard facility. There's Northeastern, I think. Well, whatever, you get the idea. So as it transpires, I discovered that, zoom in faster. Okay, so, see, this is learning through doing. So, Harvard, so this is that now owned by Harvard, Cambridge, Alston, Blackstone power plant, which featured in that Reuters article I showed you. So, I grew up as a toddler here in Peabody Terrace, whilst my dad was a poor grad student. I probably shouldn't say that one. Recording, but yeah, so and he couldn't Oh, I should also say that. But this is the cheap grad accommodation for Harvard, and this is the expensive, apparently, accommodation for Harvard. Which I don't know. I mean, obviously, it's still within the boundaries of 3 miles, and I say 3 miles because that's what the EPA. So here we go. So 3 miles, which is 4,828 meters approximately, which is this. I use this radius here because that's what the EPA referenced in terms of the impact of looking at the impact of facilities on surrounding communities. So I was breathing in that sweet, sweet air as a child. And then we did move out. We moved out to Belmont for which, is outside the 3 miles, but, it's still, there's a lot of cumulative smog and stuff there, which is fun. So, yeah, that just it kind of makes this more real, but also what about the people who still live there, under this fossil fuel behemoth? Anyway, okay, so enough of the sentimentality. Excuse me, E5. So this is that heat map I showed you earlier. It looks really pretty. It's probably the most impactful, but probably the least kind of scientific Python aspect of this. So that's why I said it was optional. But again, this is just another tool for your toolkit. Especially, I shouldn't be mean. So non-technical stakeholders, they love this. This always really gets them engaged, and then you can show them actual science. Sorry, I shouldn't be mean. So yeah, so you can go through that. It's pretty self-explanatory. You just need points, just sort of a list of points. Okay, so section F, how are we doing for time? Not bad. Okay, plot data for statistical trends. So F0. Copy df prep and assign to df trends, which we will prep for developing statistical graphs and have a look at the new data frame. So copy df, create the trends data frame. I mean, it's exactly what you expect, but just for best practice. So yeah, but you can see here, there's a geometry column. I'm going to be totally transparent. It's kind of weird. I don't know why this kind of has been added to that df prep. There might be some sort of hang up, but you do need to, excuse me, you do need to delete that. If anyone can tell me why the geometry was added to a different object in memory, then please tell me. So now you delete that. F2. The statistical graphs we're developing plot each facility separately and also separately within state subsets. It's now useful for the row labels to be meaningful rather than the integer index created by default by the original pandas read CSV call. Set the index of df trends using the existing columns facility and state, making the change in place. Okay, so, I mean, this makes more sense if I just show you. So basically now we want those 2 columns facility and state to be the index. We can then, call rows by their name as opposed to by 5, 12, 118. So set the index to be these 2 columns, facility, state. In place equals true. So now you should see that. So there. Now that's a multi-index. I mean, each of those facilities is unique, so, but then obviously you've got the state, and then that kind of tuple, is a unique combo. Okay, so F3, the statistical graphs we're developing only need the columns with stats data. Now the essential non-stats data is in the, excuse me, is now the row label. Drop the slice of columns from HGRP to parent companies. So, df trends drop. Again, sorry, this is not exciting data wrangling, but the end result I think is quite interesting. So, worth it. Fingers crossed. So, drop that slice of columns. Oops. All the rows. So, excuse me, by labels GRP, ID equals even to parent companies, which is inclusive, as you'll see. axis equals 1. So remember, it's like, look at the columns, because you're not going to find it in the rows. In place equals true. df trans, please have worked. Yeah. I couldn't remember what I was supposed to, couldn't remember what we were supposed to be doing. Yeah, so basically now, that's great. We just now have the stats data. Okay, F4. Generate one of the target statistical graphs, namely a horizontal stacked bar chart of each facility's reported year emissions, ordering the facilities by their cumulative value. That description is really, like, doesn't really tell you, as with lots of descriptions of code, it doesn't really tell you what you're actually doing. But yeah, hopefully this will be more intuitive. So, okay, you're sorting these by this cumulative column, which is why we kept it in, but we're not going to plot it. So, as I said, remember, it's always going to do ascending equals true. So there we go. See, Howard is the, only hit the threshold once and never again. Seems a little sus to me, but anyway. Okay, so, but we actually only want to plot the stats, the time series data. So use the local operator again. You just want these columns and only to 2021, not to the end, right? So then that will just select that. Then you can plot, tell it you want a stacked bar, a horizontal, sorry, this is bar, H is horizontal bar, stacked equals true, is then a stacked horizontal bar. You could run that, but try and put everything in one because this does take a while to render because it is computationally meaty. Give it a fig size, take out the legend, make the font size small because you're trying to fit 118 rows. Oh my God. So, oops. Again, that's not obviously how, like this is not massively readable. You would do other things to make that, oops, see, and that doesn't really work either. But yeah, obviously it is interesting. I'll kind of read this for you or you can see on your own. So yeah, as I said, that was MSU, unfortunately. loads of emissions every year. So yeah, from a statistical perspective, you say it's sort of there's sort of these really heavy polluters. And then, I don't know, maybe like like half of the, is that half? But a lot of the data set are actually not that much. Some of them, are every year. Some of them are only a few years. So like, who's that? Missouri was only 4 years. So there's going to be some interesting stuff if you delved into that. But anyway, just to show you stuff you can do. Okay, F5. Okay. We're on the final track for the last graph, and then we'll have another 10-minute break. F5, prepare for generating the final statistical graph, visualizing the time series of each facility, but in subplots by state, and only for the 12 states with the worst aggregate cumulative emissions. So, compute the state-level aggregate cumulative emissions. So, we're grouped by the states, which is now an index. So that, I don't think, does anything. Yeah. Pull out the cumulative column, which is also doesn't give you anything. I always forget what you can see and what doesn't. But yeah, then you can sum it, and then you've got, that's like all the facilities in each state rolled up to the state level. Again, that is alphabetical by default, which, maybe is sometimes what you want. It's not what we want. So F6, reuse the code from F5, but this time sort the default alphabetical output from worst to best, i.e. from large, excuse me, from big to small, and access just the first 12 indices, and then assign this expression to worst 12 states. So, what was I doing here? It's weird. Cumulative. Oh, okay, sorry, the formatting's just weird. Sort values. So let's now sort the values. Ascending equals false, which is in that. So no surprise, Michigan, because it's got MSU and other things. Purdue, I think. But then now we just want the 12. We just want the index, and we just want 12 of these. So index 12. which gives you that, and then save that down, worst 12 states. Okay. And then you can see that again, I mean, if you really need to. Okay. F7, assign a copy of df trends without the cumulative column to a variable df time series. So yeah, sorry, I know this is a very faffy, but you know, it will all come together in the final graph. So we want to drop cumulative. You can just drop it by label because there's just one of them. Copy df time series. So double check, because this is what we're going to make generate all the plots from. So yeah, perfect. Okay, F8, we're going to test how to select a cross-section of df time series using the multi-index we set in F2, specifically returning all the facilities in the state of Pennsylvania, and then transpose for the line graphs. So I mean, you can try any, you know, you don't have to do PA, you could try something else. But this is just to give you a sense, because we're going to use that again in the final plotting routine. So I'm just trying to show you the components. So the final result looks less weird. I mean, not understandable. So you select. So yeah. So this obviously has just selected all the facilities in Pennsylvania. And then transpose. I mean, obviously this could be Utah, which is that. Okay, so there's a bit of prep here around how the the axes work. You can read that if you need to, but we'll just go straight to F9 and make the final statistical graph. Yay. Use matplotlib to set up and generate state-level time series subplots showing the 2011 to 2021 emissions for each facility in the 12 states with the worst aggregate cumulative emissions. I swear, all these titles sound so much lengthier than, you know, it's so much more intuitive just to see it. But okay, so subplots, here we go, let's do the absolute basic. I mean, that would be nothing in it, but okay, let's show you. So remember, we've taken 12 states. We're going to arrange that in 12 plots in a 4x3 effectively arrangement. So n rows equals 4. Did I spell that right? Yes. N cols equals 3. So there we go. So your axes are just your plots. I mean, if you've worked with matplotlib, you already know this. But yeah, so 4 rows, 3 columns, and then that loop is going to generate the relevant time series. Okay, so this loop, state ax in zip. So there's 12 worst states, and the axes, which we flattened, as per the note above, flattened, and then we're basically going to loop through. We're going to go df time series, cut it by that state, which is in that, that's where you access it, in the index, transpose, plot, and plot it on that specific axis. What does it look like? Home axis. It's not defined. So that's not very useful for you to see. So I'm going to, that's why I set the fig size. And now I remember. Okay, so that now you should effectively see is it close to the end result. So, you know, 12 worst states, the time series for each facility in each state, and then the rest is just, you know, aesthetics. So share Y is just to make sure you can actually, you know, this axis lines up, because obviously, you know, that is not the same as that, even though it looks like it's on the same level because of the scale. So this is just adjustment. So share Y equals true, hence why I'm not going to type it. What else is here? So here we go. These are just, you know, give it a title. So formatting-y things. So that kind of just makes it look more, you know, readable. So there we go. Now you've got labels and bits. And this is basically just for the x-axis. So that looks kind of presentable, or is presentable. Oh, it's not very presentable there. Ta-da. 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 So yeah, that's just like I said, just to adjust the labels. And And so F9, so final bit of this session. So comment, different approaches to carbon reporting. This is your, real world interpretation. Different approaches to carbon reporting and accountability could reveal different insights. Instead of the EPA's GHGRP requiring individual facilities exceeding the 25,000 carbon dioxide equivalent metric tons threshold to report their pollution, there may be more interesting trends if this requirement was at parent level. So I'll just tell you what I was thinking here. This is your sort of boring accountability thing, accounting even. So for example here, like Yale, this is the green and the orange. Sorry if anyone's colorblind. But yeah, so they both beat the threshold, but they're obviously individual. They're still reported, but obviously if that was at Yale level, it'd be at least the sum of the two. Then of course you've got all the other things. There could be other facilities that Yale manage which don't meet the threshold, so then you're not seeing that full picture, and maybe that could be like even higher, But it's not going to be lower than the sum of these two. So that's why I'm saying that, I would bet that there's some sort of accounting, nuances which don't necessarily make the full impact of university. I mean, not just US university facilities, like any facilities. Reporting at this level, I think, could hide a lot of trends which could be pretty interesting. Hello. What was your name again? Jackie, sorry.
Is the threshold so that the data below that threshold is not available?
No, correct. Exactly. So they're literally, so the reporting requirement from 2011 was that, you meet the threshold, you have to mandatory report.
And that threshold has not changed at all since 2011, so apples to apples?
Yeah, exactly. So there's no, and I guess the other thing I probably should mention, which is interesting, within that data on the EPA, you can actually see you can see like more details, more of that kind of chemical stuff, which is not my background, but you can actually see that the majority of these facilities, sorry, this isn't necessarily to your question, but you can see that these are all through stationary combustion, so fossil fueling. You can see the fuel types, so it's basically all natural gas, gas and oil. Someone, I think it's North Carolina? One of these is coal, really heavy burning coal. Where is Carolina? No, where is Carolina? Is Carolina here? I can't remember. One of these is burning.
The middle, third one down, North Carolina.
Middle, sorry.
Bottom, right there.
Oh, yes, sorry. Yes, that's it. NC Chapel Hill. Sorry, yes, exactly. Thank you. So this one, so that's coal. That's kind of, you can see other articles online. Someone is burning tires, actually. So, there's stuff. There's like a whole stuff. So, I really hope someone kind of does more reporting and like more insight onto this because, like I said, Reuters and I both found it really fascinating. I'm sure Reuters will be pleased to know I thought so. But yeah, anyway, sorry. That is the end of the carbon pollution exploration. And if you would like to take 10 minutes, then we will return and do deforestation. Or explore deforestation. We're not going to do deforestation. That'd be very counterintuitive. Please make sure you have, obviously you can manage your files, I'm sure. But yeah, you need to have, or this tutorial is set up assuming that there is a subfolder called deforestation exp data, which has TIFFs in it. So there's 4 TIFFs, which hopefully you downloaded. This is the point where, did anyone, sorry, faffing with, okay, that's fine. Did people manage to download or install rioxarray? Or I guess maybe I should say, did anyone not manage to download rioxarray? Wow, yes, okay, sorry, I thought that might be. So yes, which don't worry, this is not a sort of shame moment. Just because, because I'll just tell you the issues with rioxarray. So rioxarray, which seems to be where the geospatial community are going in terms of raster import and export. So it's kind of, instead of using raster IO, which people might have heard of, but it does use, rioxarray does use rest.io. Rest.io requires GDAL, which is a C++ package. And that does not work very well with Windows, basically. So to that extent, if you don't have rioxarray, which is fine, I just need to tell you now, explain, and also for everyone else. So I've set the tutorial, or I've developed the tutorial, so you've basically got like the rioxarray, I think I said it in the message, you've got the rioxarray like workflow, which is just your normal stuff, but then this is there's an alternative, basically as you can say, which doesn't need rioxarray, and which is effectively a kind of pill numpy version. So for people who are doing the alternative, there is steps, sort of parallel steps for the majority of the workflow, not the last section, which is optional anyway. The difference mainly in the outputs is that because you're basically using you're just basically plotting an array of numbers. There's no geospatial dimensions to it, so there's no axes. But hopefully the idea is that, at some point, you know, in the future, you might be able to figure out how to get rioxarray. There's some non-official wheels that you can download. So anyway, just so people know, so the way I'm going to run through is, I'm not going to go through the sort of numpy version. It is there, so what I'll do is, I'll just kind of hide it, right? And then people who need to do the alternative obviously use the alternative. Does that make sense? Okay, so assuming that you do have this data, then, okay, we'll get started. We are actually doing really well on time. Well, I say that now, and then we'll rush at the end. So I was going to set the scene. So first of all, do people use spectral data? Okay, yeah, great. So one person, this is going to be really boring for you. Remote sensing stuff. If it's new, that's kind of great, because then I can play you this video, and it's kind of worthwhile. So instead of me explaining it to you, because I actually am an economics grad, I thought I would let the National Ecological Observatory Network explain a little bit of the space in which we're operating. So we'll just go. Oh. Cece, is there sound?
The properties.
Sorry, we'll just do it again. It's only, we'll just
If
do
you've
5
ever
minutes.
used a camera, then you know something about spectral remote sensing. Spectral related to the electromagnetic spectrum, which includes light that is both visible and invisible to human eyes. And remote sensing, which involves measuring the properties of objects without directly touching them. The typical camera that you use measures and records visible light that objects like trees and rock reflect. This light might come from the sun, but it also might come from other sources, like light bulbs. While we often use cameras to take selfies and silly pictures of our furry friends, scientists use high-powered cameras called imaging spectrometers to measure changes in things that impact our environment, like water quality or vegetation cover and health. Imaging spectrometers mounted on airplanes and satellites help us create maps, like this vegetation cover map for the entire United States. But how exactly do scientists measure changes to our environment using reflected light energy? To answer this question, let's have a look at the electromagnetic spectrum, which is composed of thousands of wavelengths of energy. Visible light, what we see with our eyes, is contained in the blue, green, and red portions of the spectrum. The rest of the spectrum is not visible to human eyes, but can be detected and recorded by sophisticated camera-like sensors called imaging spectrometers. Now, there are thousands of wavelengths to record in the electromagnetic spectrum. To deal with all these wavelengths, imaging spectrometers divide the spectrum into groups of wavelengths called bands. For example, a band in the near-infrared region of the spectrum could include energy from 800 to 850 nanometers. This band is useful to map healthy vegetation. The width and number of bands is what we call the spectral resolution of an image. Higher spectral resolution means more bands that are spectrally more narrow. Lower spectral resolution means fewer bands, each of which covers more of the spectrum. Now, imaging spectrometers measure reflected light energy. You see, different objects reflect, absorb, and transmit light differently, depending on their chemical and structural characteristics. For example, plant leaves are green because they reflect more green light than blue or red light. On the other hand, Fido the dog reflects more light in the red portion of the spectrum because of the chemical and structural makeup of his fur. If Fido's chemical and structural makeup was the same as a plant's, then he would look green. Now, when you point your camera towards your favorite canine doing something silly, the camera records the amount of light reflected from the dog and its surroundings in the visible, or red, green, and blue bands of the electromagnetic spectrum. The camera creates what's called an RGB image, which is composed of millions of pixels. Each pixel in the image contains a value representing the amount of red, green, and blue light reflected. We can break the image out into its red, green, and blue bands too. Here's the red band on its own. Brighter pixels mean that more light was reflected by objects in the image and recorded by the camera in the red part of the electromagnetic spectrum. The darker parts are areas where less light was recorded. When we combine the red, green, and blue bands together, we get an image that looks similar to what we see through the camera lens. We can plot the amount of red, green, and blue light recorded in each pixel to create what's called a spectral signature. In this signature, the amount of energy reflected in a particular wavelength is shown on the y-axis, and the full range of wavelengths that were measured by the camera, in this case blue, green, and red, is on the x-axis. The spectral signature for Fido is quite different from the spectral signature for a plant. This makes them appear visually different to our eyes too. Differences in spectral signatures can help scientists identify different types of surfaces and objects within images. Most cameras record light in the visible or red, green, and blue bands. However, plants, dogs, and other objects on the Earth also reflect light that we can't see with our eyes. For example, plants reflect up to 60% more light in the near-infrared portion of the electromagnetic spectrum than they do in the green portion of the spectrum. This is why differences in reflected light in the near-infrared portion of the spectrum are important for mapping vegetation on the ground. To measure these differences in the non-visible portion of the spectrum, we use imaging spectrometers, which record light in both the visible and non-visible parts of the spectrum. Imaging spectrometers produce what are called multi- and hyperspectral remote sensing data. Multi meaning many bands, more than 3, and hyper meaning up to hundreds of bands, collected at very high spectral resolution. We use these multi- and hyperspectral remote sensing datasets to measure light energy reflected from objects on the Earth's surface, and to estimate many physical and chemical properties of objects that we wouldn't see with our own eyes. We then use those measurements to classify what's on the ground. For example, pixels that have a spectral signature with a lot of near-infrared light energy are often vegetation. To review, different objects reflect, absorb, and transmit both visible light and light energy that we can't see differently. Imaging spectrometers record the amount of light that these objects reflect. The amount of light energy reflected by an object throughout the electromagnetic spectrum is called its spectral signature, which is driven by the physical structure and chemical makeup of the object. We can use that signature to identify different objects in both the photograph and across the Earth's surface. And that, my friends, is how we use reflected light energy to both map what's on the ground and measure changes in our environment.
Amazing. Okay, so sorry for the person who presumably already knows that, or other people. I should probably say that I think that person who made that, Leah Foster, I think they are actually here at the conference doing a maintainers thing, which is really cool. So I'm going to go and fan person them. Anyway, so that's kind of, we're using a lot of those concepts, not obviously all that, multistructural, hyperstructural, not all of them, but if that kind of gives you a good sense of, good context for what we're actually going to be doing. So, at this point, I should probably also show you that oh yeah, there, I knew I set it up. Okay, so, I'm just going to give you a sense of where the data came from. So I know I showed you this earlier. Has anyone used Landsat Look, access to yours? I mean, apart from that person there, for sure. So I took the data. That data is literally from this portal. It's one of these scenes, and then I clipped it, just so you know, because these are big images, and you'll already see they already take quite a while actually to load, even the clipped versions, which are a fifth of the size of the original ones. So, let me give you some of the context. Okay, so which example of deforestation are we examining? So the change from 1984 to 2022 in a 60 square kilometer region of interest, an ROI, originally covered mainly by tropical dry forest at the Brazil-Bolivia border within the Amazon River Basin. So there's more context here. So again, happily, oh, I'm so proud of myself. So, you know, I came up with the region myself. Sorry, this is a bit of a, yay me. And then it turns out that NASA had actually also examined the same region. I mean, okay, our region is slightly smaller, is here, like here, but it's that portion. But yeah, so, you know, this is obviously a relevant area. Okay, what scientific approaches are we taking? So satellite image processing and classification. So this is not your, you know, deep learning, you know, fancy bougie hype stuff. This is just, you know, handcrafted and experimental, just like I said, as a more like a prototype to show you what's possible, and then for your purposes, you can, you know, scale up as needed. So what outputs will we develop? Spectral vegetation indices, but specifically NDVI, and thematic maps, specifically of land cover, or estimated. What will our outputs tell us? So they will help quantitatively detect and measure land cover and land use, LCLU, change in this ROI, particularly the clearance of original tropical dry forest since 1984. Beyond the well-known eco-impacts of deforestation, so yeah, the whatever carbon stores, well not whatever, but what makes this example significant? Exemplifies the contrasting historical LCLU change in a biome as a consequence of country boundaries and local differences, so e.g. in forest governance, stewardship, etc. So you can also read that secondary issue, which is just interesting, but not obviously totally relevant. But yeah, what I wanted to show you was this. Now, of course, I don't know if this is real or not, before I, you know, caveat, but I just thought this was really interesting. This is, I'm pretty sure I could identify where this is on our map. But yeah, so the dry tropical forest, it seems to be, might be called like Cerrado, something. Experts would tell you, but yeah, this is the Bolivian side. This is the Brazil side. This is in the state of Rondônia. I'm sorry if I pronounce that really badly. I pronounce everything like French and Italian. So yeah, and you can see, again, if this is real, and the river, the Rio Guapore, was it? Guapore is like the delineation of the country. And yeah, so if that is real, you know, that is just really interesting to see how, you know, exactly the same biome, I mean, basically, you know, how it survives or doesn't survive, or, you know, is managed or not managed, you know, can really depend on, you know, geopolitical differences. So anyway, hopefully that gives you a sense of what the region is, not just, you know, pixels. Okay, so this is the data source. You can look into that a bit more, and some extra things on remote sensing, because like I said, that is not my background. I'm just telling you enough to be able to do the tutorial. Okay, A. Oh, I should do the table of contents. So this is where we're kind of going. Set up Jupyter Notebook and satellite data. So remember, if you've got xarray and rioxarray, we use that. If you don't, use the alternative. So import glob, I don't know. Import numpy as np, import xarray as xr, import rioxarray as rxr, import matplotlib pyplot as plt. Please work, or else this could, yes, thank you. Although I did that wrong. Okay, again, just your normal jig, the auto completion. Okay, so A2, read in the 4 tutorial files in the deforestation subfolder, also creating global variables with the same name as their corresponding file name. So how you would do your I/O would be totally up to you, so I would not stress about the specifics of how I've done this, but just know that it's basically creating now variables with the same name as the file, just about the extension. For the people who are doing the alternative, please note you have to change the extension from TIFF to TIFF for pill. I do not know why, but it works. Okay, section B. Let's inspect the satellite data. So, B intro. Raster data is one of two main types of geospatial data. The other is vector data. So the points and polygons we handled in the mapping section of the Carbon Polluters exploration are examples of this. So data stored in raster format are typically in grid matrix structure, and they render as pixels, so picture elements. For geospatial raster data, each pixel relates to some area on Earth, and each pixel value is a measurement of some real-world phenomenon. The 4 tutorial files are geospatial raster datasets, and the pixel values they contain are satellite measurements of amounts of light reflected from a single band of the electromagnetic spectrum. So spectral reflectance values, so brightness, so more light, as you saw on that scale, less light, more light, less red light, more red light. Okay, quick caveat. Okay, I won't read that because it's detailed, but basically, because we're using, effectively like an older satellite or an older sensor and then like a new one, so that, we had like maximum like temporal difference. So the Landsat 5 TM captured a different wavelength to the Landsat, or different wavelengths for the red band and the near-infrared bands compared to the newer. I would assume, again, if someone was from NASA, that'd be great if they could tell me. I assume this basically was more, the fact that they basically made the bands, I presume, more defined, so it's kind of more accurate, which probably means that this is less accurate. But anyway, it's just things to know. They're not exactly like for like, but they're still useful for our, general purposes. So B0. So let's check the dimensions of any of the 4 tutorial rasters. I'm going to check the 1984 red band. So you know how those variables, because they're created in that load step. So there's shape. So we've basically reduced it down to a two-dimensional 2001 pixels by 2001 pixel, effectively an array. So B1, check the data type of any of the tutorial rasters. So again, I'm just using the 1984 red band. And so that should be in a float, but just be aware that the original data is in from the Landsat Look portal, is in uint 16, and then there's more about digital numbers and how the raw data is collected, which is way out of scope for this tutorial. B2, try rendering the red band reflectance values of the ROI in 1984 using plot, which of course uses matplotlib. So I'll just do this first. ROI plot. Okay, now pass reds _r, so reversed reds as the optional CMap argument, and adjust the size and aspect of the plot to be smaller than the default, so as to be faster to load. Because like I said, these are really heavy. You already see those data sets are massive. Aspect equals 1.3 size equals 4. So again, you could customize that, but just to give you a starting point. So, comment, there we go. I'll just load that for it. So yeah, so I know it doesn't look like very much, we could adjust the scale, but, so remember, less light, lower reading, darker in this instance. More light, so more reflectance, like less red. Okay, so just to be clear, so that's, as that is forest, that should have lower values, as it does have lower values, because spectral signatures, the vegetation should have absorbed, the chlorophyll should have absorbed more of the red light. Then there's firing patterns here, so I'll just show you really quickly that link. This is a really interesting NASA resource just to show you different sort of agricultural patterns from space. So yeah, I think the one here, the one in Rondônia in Brazil, looks a lot like the fishbone, but again, I'm not an expert, but I'm sure you could find someone who is. So B3, there is a range of spatial metadata embedded in our rasters. Use rioxarray's bounds method to check the spatial extent of any of the rasters. So, basically like the dimensions of what we're looking at. So RI this, rio bounds. and there's just a note here that I actually clipped it specifically for these values, and they are different. Anyone who is not a geospatial expert want to have a guess why they may not be exactly the same? Why can they not cut exactly how I asked them to? Okay, this is not the exciting question. So it's because remember they're like the pixels, so maybe like it has to cut on a bound, right? On like where exactly the pixel is. And where I asked for clearly is not exactly where the pixels, the pixel boundary were. So these, I presume, are the nearest pixel boundaries. So just a little note. B4, have a look at some actual reflectance values. Extract a sample at the top left corner. So from so here, top left corner of the ROI 1984 red band 3 raster as a numpy subarray, specifically the first 5 rows and columns. So ROI, red band values, which then turns it into a numpy array. So multi-dimensional indexing, first 5 rows, first 5 columns. So there. So the rest are, it's just numbers in a grid format. There's the reflectance values. Why do I always anticipate myself? Okay, so each value, there we go. So it's a specific 30 by 30 meter area at the Brazil-Bolivia border. And this one is, these are the readings that Landsat 5 TM measured on August 13th, 1984, be precise. 30 meters represents the spatial resolution of our rasters, a metric indicating the ground surface area that forms a single pixel. Satellite sensors can have higher or lower spatial resolution. So, for example, MODIS, which is another NASA, I think, sensor, isn't it? So yeah, that's a higher spatial. Do I mean that higher, lower, higher, lower? Does anyone? Anyway, there is a larger area covered by each pixel, so it has less granularity. So 30 meters is pretty good, it seems. So B5, try rendering this numpy subarray of red band reflectance values using matplotlib's matshow function. So remember, at this point, it's literally just an array of numbers. So you can plot those, we'll render those with colors. R. So yeah, which is not massively exciting, but it just shows you that your image, if you don't do any sort of this kind of digital signal processing stuff, images are just numbers. Okay, optionally, this is just again to kind of give you more of a sense of what the data is. If you run that, I've just plotted that really quickly so you can, again, I'm just reinforcing the concept that brighter colors are higher spectral reflectance values, and then lower is darker. B7, okay. Don't worry, it does get more interesting, I think, but I just kind of need to give you some sort of basic concepts. As the area of the ROI in 1984 covered by the pixels in the top left corner is not overly interesting, let's have a look at the top right corner instead. So we'll do this again, values. So this time, top right corner, we're going to look at -5 to the end. CMAP, again, is the reds are. Okay, so there's that. Now, as I said, start by visualizing a 5 by 5 matrix and then keep increasing the size up to 500 by 500 because, because I've tested it and it looks fun. So now you've got 50 by 50, and you can start to see. Again, remember, each of these is 30 square meters on the ground. And then if you start, again, just kind of zooming out. So this is where you can really start to see some of the. Remember, this is 1984 already. These are those, I'm going to presume, agricultural driven deforestation, sort of rectangular plots in that sort of fishbone pattern. And then, you can move out a little bit more. So yeah. Again, like I said, we're just trying to show you the the relationship. Oh, hello. Sorry. Oh, I see. Yeah, sorry. So you want to try a different color map? Yeah, of course. underscore earth, like that. Oh, oh yeah, the gist, yep. Is it that? Ooh. Oh, cool. Yeah. So yeah, you could definitely, yeah. Honestly, I I was like, oh, I really want to like, you know, do a sort of kid visualization, sort of, you know, satellite image art sort of knockoff from this, because I think there are some really interesting things. But yeah, sorry. Anyway, we'll move on. So F7. Did I do this? Agricultural patterns. Okay. Okay. Yes. Yes. Yeah, exactly. So the spectrum, I'll tell you what, actually, I'll just go to the next section because I think that will help reinforce your point. But yeah, sorry, I was trying to stress it because it can be confusing. So section C, prepare to calculate a spectral vegetation index. So C, intro. A spectral index or ratio is an indicator of some phenomena such as biophysical or biochemical properties calculated using the different reflectance properties of different objects. So to this person's point, Landsat data products like burn ratios and moisture index are examples of spectral indices. One type of spectral indices relevant to deforestation are vegetation indices, VI, the most common of which is the normalized difference vegetation index, NDVI, used to quantify vegetation greenness. So NDVI utilizes certain reflectance properties of plants. So chlorophyll strongly absorbs red light. So lots of forest means lots of red light is absorbed, so not so much red light reading. Whilst leaves/plant structure strongly reflects near infrared light. And so that's the spectral signature of plants. So the formula to calculate NDVI therefore requires the reflectance values in the red and the near infrared bands. So there, I don't know. Yeah, I hope that's kind of fairly intuitive there. So, or is it intuitive? Okay, maybe we should talk about it. Okay, so if it's plants, right, if there's like more green, if the surface, that 30 by 30 meter is just like thick, dense, totally green stuff, so it means that it will have the plants, because plants and leaf structure strongly reflects near infrared light, this will be really high. And then if there's plants, the chlorophyll strongly absorbs red light. So this should be high, that should be low. So there should be, you know, that minus that should be large. And then that over that plus that obviously normalizes it. And then if it's like like water or concrete, I think stuff like that, then I think basically they're about the same, so then you don't really get a difference. So then your reading is much lower than if it was plants. But hopefully that will make more sense when we actually do it. So by design, NDVI values therefore range from -1 to 1. Negative values to 0 indicate no green leaves, whilst values approaching 1 indicate highest density of green leaves. And there's some like NASA NDVI training. I mean, there's lots of NASA training, but yeah, that's a one which I think is more accessible. In section D, we will calculate NDVI values for ROI to help detect how the existing tropical dry forest cover in 1984 had changed by 2022 as likely deforestation. And then just to note that you can get this pre-calculated, but you know, it's better that you do it yourself because you understand it more. So C0, in advance of calculating NDVI values using the above raster math formula, render the red and near infrared rasters of the ROI from 2022 as subplots. So we're basically plotting the two rasters from 2022 side by side, just so you can get a sense of what the data looks like before we calculate the NDVIs. So red band, we'll do red band on the left. So plot. Then we'll do the near infrared band on the right. Plot. Okay, and I'm just going to copy this because there's no value in you watching me type that. So blues. That also needs to be on that axis, and then plot show. No. subplots. There we go. Schnell, schnell, schnell. There. Like I said, it really does take a long time. So yeah, so this is 2022, right? So the one you saw earlier was 1984. So I mean, you can see even from the red band, like, I mean, you know, even as like a non-scientist like me, I mean, it's pretty clear. This, you know, again, this is the Brazil side. This is the Bolivia side. I'm pretty sure that that photo I showed you, I think it's somewhere, possibly here, one of these kind of tributaries of the stream. So, yeah, it's yeah, not a lot of trees left on that side, clearly. And then, okay, the near-infrared, this will not be particularly interesting itself. It's like, as we said, the combination of the two. But let's start actually calculating some NDVI. And I'll just tell you, so we're calculating this, we're going to make some maps, then we're going to do some thematic maps, and then there's some optional kind of relation to the real world thing at the end, if we have time. So, D0, calculate NDVI values for the ROI in 1984 by performing the required raster math with ROI 1984 near band 4, and then ROI 1984 red band 3, and assign to NDVI 1984. So, the kind of most important bit, I'd say, is actually the easiest, because of the power of numpy and vectorized operations. This is a piece of cake, and I say that now, and I hope that this doesn't fail, and I haven't jinxed it. So, the near-infrared band minus the red band over the near-infrared band plus the red band, which I'm literally just going to copy that. Oh, I'm doing the wrong date. 1984, 1984, 1984. Okay. I knew it. I said it was the easiest bit. I totally jinxed it. And then I messed it up. Okay, so you've now got NDVI 1984. So let's sense check that by looking at a couple of values. NDVI values, turn it into a numpy array. Let's just look at some 2x2. Just a sense check. So yeah, so in that particular corner, that top left corner, you're looking at sort of, 0.3, 5, 0.4. So that, we'll talk about that later, but that is sort of like some veg, sparse veg, not like super dense, but veg. D2. So calculate the NDVI values for the ROI in 2022 by performing the required raster math with the ROI 2022 near band and ROI 2022 red band, and assign to NDVI 2022. So basically the same thing, but for the other time period. So near infrared minus red over near infrared plus red, that's right. Yes, good. D3, so also sense check that. 2x2. So, I mean, just by coincidence, or maybe usefully, so these values are lower, which, again, I wouldn't draw a massive point about it, but, you would basically say that that could indicate that where in 1984 there was more veg, maybe in 2022 in the same spot, there looks like there's less veg in these 30 square meter areas on the ground. D4, this is just so you know that you can save stuff. You can export stuff, so you can do that. I already have 5,000 copies of these, so I'm not going to. Okay, section E. So now let's just make some maps from that data. E0. The NDVI datasets are still geospatial rasters, i.e. grids of pixels, and still each linked to 30 square meters on Earth. However, the value of these pixels indicate the density of green leaves covering that place on Earth on a scale of -1 to 1. So not just measurements of light as before. So let's therefore render both NDVI rasters to help discover how dense vegetation was in our ROI in 1984 compared to 2022. So this is your classic before and after. Which I probably shouldn't read in the suppliers. It may not be quite what you expect, and that's where I'm going to say this is possibly down to the change in band coverage of the different of the older and the newer sensors. However, you know, I mean, that's science, right? Like, you don't always get the results you're hoping for, and if you're ethical, you're not gonna jig them just to make it show you what you want. So plot, show. Yep, plot, show even. So this again is just the same CMAPs, putting on the axis, but here I'm just specifying. So instead of actually having -1 to -1 as the scale, I am jigging it a little bit just so the colors stretch a little better, because that's the sort of range of the values in these two rasters, NDVI rasters. So, okay. So, you know, this is real data, so, you know, yeah. Obviously, I would have liked this to be like really, really, you know, really green, and that would be really, I don't know, not. But again, you know, you're using different data, so not like for like ways of data collection. But, you know, there's still things that you can see. So what can you see? I mean, here you can obviously see, so, you know, this is going to be lower NDVI values because this is presumably like earth roads that are created to in order to create the farming plots, and then they've obviously kind of really gone to town with more clearing of the forest, but also, you know, plotting, growing crops, that's what I meant, crops, which are also green. So then, you know, if you want to do more sophisticated analysis, you would, you know, want to try and figure out the difference between, you know, crops, greenness from like crops and greenness from like forest. So I'm sure an expert could tell you that. I think something for me, what I thought was interesting actually was that there does seem to be, so, you know, it's not just like, you know, you're clearing the forest and, you know, carbon sinks and stuff like that, but also when you don't have trees, then you get more runoff and, you know, there's more sedimentation, goes into rivers. You know, I'm just guessing by eye, like these rivers, they kind of look a lot kind of weaker here. Some of them kind of like the loops are kind of cut off. That would sort of make more sense to me, that there's more kind of silt, like effectively river pollution. So anyway, things. There are things you can do, things you can see. Here we go. This is the caveat reminder, but the thing which we can use is, I'll just read this. So this is about the NDVI values of what surfaces or what materials have what kind of NDVI values. So areas of barren rock, sand, or snow usually show very low NDVI values. Sparse vegetation such as shrubs and grasslands or senescing crops may result in moderate NDVI values. High NDVI values correspond to dense vegetation such as that's found in temperate and tropical forests or crops at their peak growth stage. Anyway, and then the other remote sensing things. Other sciencey things. Okay, so E1. So far in this exploration, we've been handling continuous raster data. However, in preparation for developing a thematic land cover map next section, let's start to consider how we could meaningfully group or bin pixels into NDVI ranges associated with specific land cover. So check the distribution of both sets of NDVI values through quick histogram plotting. So let's literally just look at those values on top of each other. CI plot hist, not hits. So you can just plot that straight away. That's not super useful. Let's give it some colors. Blue colors. And then also we're going to give the 2022 plot some transparency with the alpha value, just so you can actually see stuff. And then this semicolon is just to suppress this weird stuff. I mean, great stuff. Thank you, matplotlib. So again, I mean, this is I guess what I was hoping to see when I designed or, you know, came with this. I was like, oh, hopefully in 1984, you know, these values will be like way over here. And then in 2022, they'll like be way over here. And it's not quite like that, you know, I don't know. There's also things on the day, the angles of the satellite, all that kind of stuff. But I mean, you can see though, this is a lot, there's a lot more here in this area than there was in this NDVI, this range of data than there was in 1984. So I'm like, this feels like the agricultural bits. Okay, so now let's do the classification. We're classifying land cover using NDVI and make thematic map. Okay, so this is like caveat. So this section is designed to introduce the idea of pixel-based image classification of land cover using satellite imagery in order to create thematic maps, and does not represent best practice. So check out more NASA training material. There's lots of it. Although I would like to say though, the NASA training material, so they actually use QGIS mainly. So I would like to say this is kind of more, more kind of Python-y. Although obviously QGIS is great, I'm sure. We will be executing an experimental process trying to develop a meaningful thematic land cover map of our ROI in 2022, leveraging known NDVI values of certain land cover and the distribution of empirical NDVI values. So, sorry. Central to this process is performing pixel-based classification. We will have a go at producing a map that describes 4 land cover types by implementing the below experimental classification scheme, whereby every pixel will be assigned to a class based on its NDVI value. So like I said, this is really just, just an idea of how you could do it. You could obviously design the classes differently, call them different things. But, it's just to give you a sense that actually sometimes simplifying the information, so from continuous to, discrete, is actually more useful for being able to interpret things. So, F0. Find out the official type of the NDVI 2022 object, because we have actually been using xarray data arrays, but I have not been sort of emphasizing that because we're not going into it, because it is a bit confusing if you're just starting out with scientific computing. But just know that it's a data array. F1, so we're going to make a copy called LCLU, NDVI, which is what we are going to basically bin the pixels. F2, our approach to implementing the pixel classification involves manually binning the subset of pixels that belong in each class, so the process is more transparent. Try calling xarray's where function in order to test replacing the NDVI values in LCLU, which are under 0.3 with 99. Okay, so this is just to show you the method that we're going to use in order to do the binning. There are much more there are other ways to do this, but this is kind of a really transparent way. So here we're basically saying the NDVI values which are under 0.3, replace it with 99. I mean, just arbitrary, just because you want to see. And if it's not under 0.3, just leave it as is. Okay, so here you go. This is a a data array, which I have not showed you because I didn't want to, because it's got things called coordinates, which are not actually they're confusing. But just so you know, that is what you're working with. And there we go, 2000 by 1 by 2001 pixel size. So here, actually, it does turn out that actually those values in that top left corner do mainly seem to be under 0.3. So that's why you get 99. So anyway, once you've tried that, you know how that functionality works. Now we're going to replace, we're going to bin all the pixel values. So F3, build the final data array output, LCLU4, through creating a series of incrementally updated data arrays that replace the pixel values assigned to each class with 100, 200, 300, and 400 respectively. I wouldn't type this out manually if I were you, because like I said, the way you might do this is differently. I mean, really, you would probably use np digitize and then a ufunc, just FYI. But this works. And you can see you've replaced here the values under 0.15, and then the values under 0.25, 4, and so on and so forth. So that works. So F4, let's review the fully classified raster LCLU4, representing our land cover map by generating a quick plot. So now you've literally just got 4 values, 100, 200, 300, 400. They're not meaningful, they're not supposed to be. It's just so that you can separate them out and color them. And color them like this. So again, it's not actually continuous. It's not a continuous color, so don't worry about that. But like I said, it's just a quick, dirty plot. So you've got the 4 colors. This is the default. So this is your higher. Yeah, that's right. So this is. So remember, this is like your low NDVIs, your highest. So that should be your most green, least green. So most green, which is correct because this, this is like the null kemp. It's a conservation like project. So there should be forests, unless, or they're doing a very bad job at conservation. This is actually rock, so that should be low. And then these like crops. There's like a couple of buildings, I think. But yeah, so that kind of looks sensible. Not perfect, but like I said, this is just to show you how it could be done, and then you can tweak it yourself. F5. So I'll just tell you what we're doing now is we're going to create our own color map and just sort of make a kind of more usable version. So F5, let's prepare to construct an upgraded version of this land cover map. Import the listed color map class from matplotlib colors. So matplotlib colors, import listed color map. So F6, create a custom color map consisting of 4 appropriate named colors called LCLU CMap. So LCLU CMap. Listed. So yeah, so this is like literally the color maps that you've been using. Like someone else has literally gone, oh, it's going to be like red, orange, yellow. So this is you just making your own, which is a useful skill anyway. You could obviously choose your own selection. This is just things which seem to look good or appropriate. Forest green. Yep. And then you can make the upgraded land cover map of the ROI from 2020 using the LCLU CMap and other matplotlib options to fine tune. Okay, so let's build this up again from basics. Fig ax is subplots. Fig size, just make them all like that. 8 by 6. So your absolute basic LCLU is you need that final classified raster NDVI. We're going to give it that CMap we just customized. That one. So this would be your absolute. I mean, this will work. This will be your classified land cover map with those colors, specified colors, and then the rest is just tweaking because like we don't, like I said, that 100 to 400 were just random values. It could have been anything. So this is where the tweaking happens. So I'm not going to type that because it's not very exciting. And you might do it differently if you are using a different visualization package. So that just gives you some actual labels. And then I think that's, yeah, you can get ready to, export that as per the other things. But yeah. Okay, so we actually can do this last bit. I think this is actually interesting. So this is the last section, section G. Transform coordinates from different map projections. So I was like, should I read this? Okay, I guess basically the point is, it's like, so this is cool, we can do stuff within this, but you're like, if you want to kind of basically like cross-reference this with something actually in the world, So you've got coordinates of this area from some other map, but they're in a different map projection. You're like, how do they, what's the relationship between these coordinates? So I'll just kind of show you like I said, this is optional, so I'm just going to show you kind of the bare bones of this. So what I did was I went to this map Biomass. So this is the Brazilian Annual Land Use and Land Cover Mapping Project, and basically identified, oops, I have to remind my Portuguese, I think it's this one. So this, I basically was looking to see what someone knew about this area so that we could then translate it into our analysis and then annotate our land cover map. This is really slow. But yeah, I mean, if you are looking at this particular area, this is quite interesting. And maybe it's a nice change not to look at Jupyter Notebook for a second. State, Hondonia, let's just do that. Which, yeah, if I was going to say, this is a really interesting tool that I stumbled on. I remind myself what I need to do. Oh yeah, okay, pasture. I won't go through all of that because you've got the steps, but yeah, this is really interesting because it can show you, you know, obviously people who actually research this can tell you what these things are. Sorry, let me just remind myself. Click natural and anthropic use. Deselect anthropic use. Okay. Okay, that's right. So this is as of 2021. So this is where this project said there is forest. And this is, according to them, which is obviously a much better source than, you know, me who knows nothing. Oh. Hello. Oh. Well, okay, that's supposed to come up with something. I can't see it. Is it slow? Okay, anyway. So there's instruction I can show you, yeah, in the Jupyter Notebook you can sort of see. But yeah, the point was, using these maps, I identified a point, I think it's here, 30, I'll just show you here, 1355 and 61. 30, 15, 5, and 61. There was somewhere here where you could actually see from 2018 to 2021, it looked like it was new pasture. Oh, here. Finally! Seriously, like I'm doing a live coding demo. Do you mind? No, I'm joking. So yeah, so here in 2018, this is it. So okay, you can already see like there's bits of, so this is pasture, I'll just tell you. Yeah, there's bits of the forest being cleared for pasture, past the gem. You can actually change that to English. I probably should have done that. And then, actually, as you slide this around long, you know, you can start to see more yellow, more yellow, more yellow. So, you know. So anyway, so this coordinate, this is at minus 1355 and minus 61. So you're like, okay, well, how does that relate to, you know, this map projection we've been using here? Like, there is no 13, you know, there's no 1355, 61 because it's on a different coordinate system. So this is just really quick steps. I won't talk through them because they're not particularly exciting on their own, but this is just to show you, give you a process of how you can convert if you've got coordinates. So these coordinates which are in the standard map projection, which is EPSG 4360, is it? 4326. I was close. So most things are in that. The satellite data isn't. So in fact, the satellite data is in this, EPSG 32620, which again, you don't particularly need to know, but you just need to know that they are different. So it covers this area of land, which is, you know, that Brazil border. So this point of interest, PRI, those are the coordinates. So I'll just literally whack this in just to show you this is a method. You could just replace it with whatever other coordinates you're interested in. You need to do some sort of transform thing. You need to apply the transform thing. And then you've actually got your transform coordinates. So there is coordinates minus 1355, minus 1355, and the 61. I think this is the 61, and then this is the minus 1355. Right, so remember xy, because this, I'm going to stress it again, this is not in xy, this is y, and that is x. So you have to remember which way around. But anyway. Then, just to show you, at that coordinate, let's see what the NDVI value is. So 0.38. So actually it's quite high. That's surprising, because it's pasture. But okay, well, it is what it is. And then G8. So you can copy the F7 plotting routine. Okay, I will do that just to show you how we're annotating, because I said we're annotating. So the F7 plotting routine, there. And okay, I'll just change the size just to make it bigger. But literally all we're doing is this annotation here. I mean, you could put it anywhere, but I guess I said I'd put it there. So annotate, 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 new, deforestation for pasture, and then at this xy And then, yeah, the rest is just kind of like, arrows and bits. So I'm not going to, I'm not going to put you through that, having to see that, but yeah. Obviously, the point is that you generated the XY coordinates, so now you know where that is. Invalid syntax, because it does not have a closing paren. Please work. Thank you. So, yeah. So that is how you can annotate, a way of translating something from, a different map, for example, or a different projection, but you want to annotate your satellite data derived output with, a thing. And that is, thankfully for me, that is the end of the coding of the tutorial. And I think, yeah, so we've got 6 minutes for wrap up, which I didn't really prepare because I wasn't expecting actually to be able to do any wrapping up. So yeah, I guess we should just do questions. That's probably more useful than me just like trying to come up with something interesting. Anything? Any comments? Something? I don't know. No? Yes?
So if you're dealing with two different sets of satellite image data, and you're worried that there might be a discrepancy with the technology that was used or the quality of the camera or whatever, would you consider normalizing dataset 1 off of dataset 2, given an area that you know hasn't changed or something like that? Like, would you consider doing some pre-processing on one, or is that getting a little too dangerous? Manipulation.
When you said, so do you mean not using two different satellites?
So, using the two, but let's say you're noticing on one that the colors are coming out a little bit lighter. Like there's just kind of across the board, you're not getting the data that you would have expected. Would you consider comparing an area that you know hasn't changed with satellite image 2 and be like, okay, so across the board on this one, we should lower values by 6 or whatever because they seem to be a little bit lighter in this one.
Oh, I see. Yeah. So are you sort of saying would that be a valid?
Yeah, would that be a good research step if you're doing this kind of thing?
Yeah, I was going to say, I think there did seem to be a lot of, obviously totally covering the tutorial out of my experience, but I did see there was a lot of people referencing adjustments, so the corrections, and I think that would, it sounds like often it is just going to be on that sort of case-by-case basis, as you say, like a region that and it's actually maybe we can make that own sort of manual adjustment of, So for example, you could even see in that the difference in the wavelengths, so with the red band, you could see it was tighter this way. So, maybe you could adjust the data and be actually, we know the values, maybe some of these values, based on the things we know about the surfaces on the Earth, maybe we know that that's kind of over, overreading, and because it's rock versus plant or something. So yeah, sorry. The end was yes, I think so. It seems like that's how people do it. So yeah, I hope that's helpful.
Yep.
Question? Where's that? Oh. Is there another question? Okay. No, that's fine if you don't have, because it's been a long session for me. Anyway, yeah, thank you for coming. I hope that was useful. If you want to, I don't know, if you want to ask me stuff about it, I'm all over the internet in a professional way. So yeah, just feel free to reach out. But yeah, thanks so much for coming, and have a great rest of conference.